Scientists think there might be a huge onion chilling somewhere out there in space. Not an actual one, but it's something even crazier. These are stars stacked inside each other, layer upon layer. These fascinating objects, called gravastars, could even be cousins of black holes. But most importantly, they might hold the key to understanding some of the most mysterious puzzles in the universe, dark energy, and even other dimensions. Let's start with gravity. Over a century ago, Albert Einstein helped us understand how gravity works. Turns out, it's not just something that pulls things on Earth and makes apples fall on Newton's head. It's much wilder. It's about warping the very fabric of existence itself. Let's say you toss a heavy ball like a bowling ball onto the middle of your bed. What happens to the sheets? They dip, don't they? They stretch and sag around the ball. Now, if you roll a smaller ball like a marble across the bed, it doesn't move in a straight line anymore. Instead, it starts circling the heavy ball, rolling closer and closer as if the heavy ball is pulling it in. That's gravity. But instead of bed sheets, we're talking about the fabric of space and time itself, or space-time for short. Heavy objects like planets and stars make dents in space-time, and moons, planets, or even light move along these dents. Gravity is the curve that tells them where to go. In that case, you can guess that black holes are like the ultimate heavy balls. The heaviest, in fact. The gravity is so strong, it shrinks them, making them smaller and smaller. So tiny, they could fit in the palm of your hand, but with the mass of several suns. Some of them are like holding over 40 billion solar masses in your palm. It's ridiculous, but they basically create a bottomless pit in space-time with insane gravity. This area around them, called the event horizon, is the most horrifying thing ever. It's a point of no return. Once something gets there, it can never escape being eaten. When something falls past the event horizon, it can't climb back out, not even light. Which is why they seem like, well, black holes. But gravastars, they're something much weirder. Just like black holes, they're probably very compact. But instead of being tiny pits of endless gravity, they might have something wild at their core: dark energy. This is one of the universe's biggest mysteries. Dark energy, this invisible, mysterious something that seems to be pushing the universe apart faster and faster. It's like a polar opposite of gravity. While gravity tries to pull things together to slow down the expansion of the universe, dark energy is trying its hardest to make our world even bigger. Luckily, dark energy has been winning so far. Otherwise, we'd all be in some deep pit. But if we can explain the gravity with balls, then what exactly is dark energy? A force, an energy field. Something else? We have no idea. Scientists have seen its effects. They know that it's incredibly spread out everywhere, but they can't tell you what that thing even is. But if it's trapped inside of gravastars, maybe we'll finally discover the truth. This name stands for gravitational condensate stars. Gravastars were dreamed up by two physics professors, Paul Mazur and Emil Matola, in 2006. They tried to think, what else besides black holes could happen when a massive star collapses on itself? That's how they created this alternative. Think of it this way. Gravity pulls everything inward, making super heavy objects like stars shrink in size. The more the star shrinks, the denser it gets, and its gravity grows stronger. After some point, it can cross a critical threshold and become a black hole. But what if there was dark energy inside to counteract this? At the core of a gravastar, there could be a region filled with false vacuum or dark energy. This energy would push outward, fighting the gravity. It's like the unstoppable force meets an immovable object. Thanks to this, the star core doesn't collapse into a black hole. Sounds wacky. We don't know what dark energy even is, so how can it fill up anything? But luckily, Even if scientists can't fully explain dark energy, they still have strong mathematical models to check how it works in our universe. So, they decided to test this theory. Here's where things get even weirder. The new theory says that gravastars might not be simple lone objects. Instead, they could be stacked one inside another. Each one is like a layer with its own dark energy bubble inside, surrounded by a thin skin of matter. The outermost shell would hold a smaller gravastar inside it, and that one could hold an even smaller one, and so on. It's like a series of balloons, one inside the other. The air pressure in each one of them is stable, evenly spread out. Thanks to that, none of them deflate. They coexist without one popping or collapsing the others. In the case of gravastars, the air is dark energy, and the rubber is the shell of matter surrounding it. It sounds crazy, but it actually makes this whole idea more realistic. A single gravastar might have a very thin shell of matter, but the thicker they are, the more likely it is to exist in a stable way. And finally, the coolest part about them is that they could explain one of the biggest mysteries of our world: how universes are born. When a star collapses into a gravastar, the matter could theoretically implode through the center and create a new dimension. This would connect these objects to the Big Bang itself. Some scientists even speculate that dark energy could be the energy exchanged between our universe and a child universe that's created from a gravastar. Of course, these are all just speculations for now. But where are all those gravastars? And how do we test this? Well, physicists aren't sure either. They're more of a what-if thing than an actual object that they discovered. Those two professors just tried to imagine what would happen if gravity and dark energy worked together like this. For now, the LIGO, a big observatory which detects ripples in spacetime, hasn't found clear evidence of gravastars. Another problem is that gravastars would only be stable in specific cases. For example, if they spin too fast or their shell will be too thick, they might start to wobble or break apart eventually, though it could actually take billions of years. Plus, even if we don't see them right now, remember that this is exactly what happened to the black holes themselves. When Einstein published his groundbreaking theory of general relativity, another scientist, Karl Schwarzschild, took his equations and found a solution to them. And that's when he realized, if gravity becomes incredibly strong, the light wouldn't be able to escape, and this could create a sort of hole in space. Einstein even thought that this sounds too weird to be true. It took many years for us to confirm black holes' existence, and we finally took a photo of one just a couple of years ago. You might remember that blurry picture that blew up online? It was Sagittarius A star, an incredible supermassive black hole in the center of our galaxy, Milky Way. So that's why scientists approach gravastars so seriously. And since all the math checked out, which means that these objects are actually possible in real life. Now, we just need to see if they're somewhere out there. What's interesting is that they'd probably look like regular black holes. They could emit high-energy radiation as they consume matter. They might even produce something called Hawking radiation, a type of energy that escapes from black holes. In other words, it would be nearly impossible to tell the difference. But gravastars have a small trick up their sleeve. If their shell is transparent to light, they might bend light in a slightly different way than black holes do. So maybe if they check the way light is bent around the mysterious object, they could spot the difference. And even if it turns out that gravastars don't exist in our reality, they're still valuable to science. They still taught us more about gravity, black holes, and the limits of relativity.
Okay, it seems scientists have come across a strange object in space, and they're not sure if it's a star or a planet. What we do know is that it's located 1,400 light-years away from us, and it makes us question what we thought we knew about the universe. Let me explain the dilemma here. We can tell if something is a star or a planet by considering the object's mass or the amount of stuff it has. Stars have a lot of mass, which gives them strong gravity that squeezes them tightly. Squeezing creates high temperatures inside them, causing them to shine brightly. Planets have less mass, so their gravity is weaker. They don't experience the same squeezing or high temperatures as stars. Instead, planets shine because they reflect the light from their stars, like our beautiful Earth does with our Sun, too. And this weirdo falls somewhere in between, since we consider it a brown dwarf. It's a special type of big, gaseous protostars. Brown dwarfs are usually like Jupiter in terms of their atmosphere, but they are much larger in size, about 13 to 80 times. If a brown dwarf has more than 80 times the mass of Jupiter, it can start burning regular hydrogen, just like a star. That's what usually makes stars shine brightly. But normally, brown dwarfs are not as hot as stars. Their inability to burn hydrogen has even earned them the nickname of failed stars. They burn at around 4,000 degrees Fahrenheit, which is cooler than most stars. But this object defies the norm. Its temperature measures an incredible 13,900 degrees Fahrenheit. Now let's put that into perspective. The hottest day in history was reported to happen in Death Valley, California, more than 100 years ago, with a temperature of 134 degrees Fahrenheit. People back then must have felt like they were melting along with everything around them. Now imagine getting closer to the Sun, like taking a trip to Venus. Venus can reach insane temperatures of 860 degrees. It's not only about the distance, though. Mercury is the planet closest to the Sun, but it's still colder than Venus. Venus is extremely hot due to the greenhouse effect. Did you know that Venus could have been a delightful place to live a long time ago? Or at least be home to any form of life. But at some point, it started to trap carbon dioxide and eventually created this thick, smoggy oven that doesn't release heat. And that's why it's so hard to explore. The longest a probe managed to last on Venus was 2 hours. But hey, that's longer than I can do at work, and then I melt. So yeah, then you get to the Sun. Its surface burns at an incredible 9,930 degrees Fahrenheit. And what's fascinating is that this weird brown star we're talking about is hotter than that. I mean, it's not hotter than the Sun's core, whose temperatures go up to 27 million degrees, but it's still very impressive and unusual for a brown dwarf to be this hot. At least that's what everyone thought until they realized why it was happening. The brown dwarf is remarkably close to another star that falls into the category of white dwarfs. They're so close to each other that our mysterious star makes one orbit around its white dwarf friend in just 2.3 hours. Woo! How old we'd be over there! Since they're this close, they're tidally locked like our Moon and Earth. That means one side of this brown dwarf always faces the white dwarf, and the other side is forever in darkness. Because of all this, our brown dwarf is superheated on one side only. So its day side is what got us confused. While the temperature on the night side is what you would expect from a brown dwarf. But these extreme conditions won't last long. Such a hot temperature makes the molecules in the dwarf's atmosphere break apart into individual atoms. And while its molecules are falling apart, this brown dwarf is slowly disappearing. And if you think this brown dwarf is hot, what would you say about Eta Carinae? It's a star located about 7,500 light-years away from Earth, and it belongs to an elite group of stars we call luminous blue variables. One astronomer first noticed it in the 17th century, but back then, it was just a regular medium-bright star. Almost 200 years later, another astronomer was observing it. But this time, it was a very bright star, one of the brightest ones in the sky. A few years later, it reached the highest level of brightness in a big event called the Great Eruption. When it happened, the star could be easily seen in the night sky. It released so much light, as much as is emitted in a supernova explosion. and remain like that for a couple of years, which is not what usually happens with exploding stars. After the party reached its peak, the star decided it was time to leave. It's still hesitating though, so it's still alive but dimmer than before. There's a nebula around Eta Carinae too. It is a shell made of gas and dust that formed during the Great Eruption. It even blocks some of the star's light. Eta Carinae is a binary star system. That means there are two stars that orbit around each other. One component has a temperature of about 26,500 degrees and the other 62,500 degrees. The main star in the Eta Carinae system, which is the more massive of the two, is 100 times heavier than our Sun. Because of its enormous mass, scientists predict that this star may eventually explode in a powerful event known as a supernova. But not for another several thousand years. So, by now, you might have already guessed what the hottest thing in the universe is. Ta-da! A supernova. The supernova is what tells us that the life of a star has ended. We're talking about the most powerful explosions in space. They happen when a star that's between 8 and 40 times more massive than our Sun flops. Its core can no longer create enough energy through a process called fusion, so the star can't even handle its own gravity. It's like a stellar burnout, too much work a star can't handle, and its core just collapses. During a supernova, the temperatures in the star's core can get 6,000 times higher than in the core of the Sun. Or sometimes, a specific type of star called a white dwarf suddenly restarts its nuclear fusion, and bam, you get a supernova again. Kepler's supernova happened at the beginning of the 17th century, and it was the last really big supernova event we directly observed from Earth. On average, supernovas in our galaxy happen 3 times every century. I mean, we got a smaller supernova in 1987 too, when a blue supergiant exploded in one of the Milky Way's satellite galaxies, which we know as the Large Magellanic Cloud. This explosion was so strong, people could even observe it with the unaided eye, even though it was incredibly far, 168,000 light-years away from our home planet. What a topic for summer days, huh? But check this out. We can also talk about the hottest thing people have ever created, made in a surprising place, Switzerland. Nah, we're not talking about a super hot chocolate. A group of scientists there created a subatomic soup called a quark gluon plasma. In this experiment, the temperature got 250,000 times as hot as the Sun's core. The purpose of this experiment was to recreate the conditions that existed shortly after the Big Bang when the universe was still in a state of chaos. Okay, let's get even more extreme. In theory, things can get even hotter. Have you heard of the Planck temperature? It's an insanely hot temperature with numbers so high we can't even imagine. A supernova is like tepid tea compared to this madness. And who even knows what the matter does at these temperatures? Okay, I'm done. Now we take you back to your regular universe. Bye now. Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics, and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close. including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own Sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now, imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature. They're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of two black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.
It happened long, long ago, and far, far away from our planet, all the way across the universe. A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Watching this fading light, astronomers on Earth noticed a strange infrared signal. It was invisible to the human eye, but could be perceived as heat. After examining the phenomenon with X-ray, radio, optical, and infrared waves, the astrophysics team made a shocking conclusion. It seemed that people had finally seen a newborn magnetar for the first time ever. This magnetar was likely formed after two neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22nd, 2020. But I'm getting ahead of myself. How about we first figure out what these novas, magnetars, and neutron stars are? Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. By the way, when a star similar in size to our sun runs out of its fuel, it turns into a white dwarf. It expels most of its outer material, and only the star's hot core remains intact. Such a core usually gets heated up to 180,000 degrees Fahrenheit. A white dwarf is just a bit bigger than our planet, but half as massive as the sun. In other words, These stars are some of the densest objects in the universe. A white dwarf can be 200,000 times denser than the Earth. It usually takes a white dwarf over 1 billion years to cool down. Under certain conditions, such a star can erupt, and this event is called a nova. It's way less bright than a supernova or even a kilonova, which occurs when two neutron stars, or a neutron star and a black hole, merge into each other. Anyway, back to a supernova. If a star is large but not massive enough to turn into a black hole, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our Sun is almost 865,000 miles across, which is 109 Earths put side to side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our Sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. That's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's an exotic form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. Neutron stars are weird and scary. Their interior is a never-ending dance of particles in extreme conditions. It results in unexpected and odd structures. For example, closer to the surface, hundreds of neutrons form blobs. Those are not unlike some weird kind of space nochi. They mold into long chains once you go deeper. Not that you'd ever be able to explore a neutron star from up close. These long chains look like a layer of spaghetti. Underneath, there's a region of even more extreme pressures. That's where our spaghetti turns into lasagna sheets, since we've started on this pasta comparison. Finally, under all these layers, even lasagna loses its form and becomes a shapeless mass. But even in this mass, there are some tube-shaped gaps. And don't they look like ziti? Another thing about neutron stars, they're spinning non-stop. And this spinning is fast, more than several hundred times per second. The fastest spinning neutron star makes more than 700 turns per second. That's 42,000 times per minute. Neutron stars also have incredibly strong magnetic fields. That's why, if there was life on a neutron star, it would be two-dimensional. The star's gravity is so powerful, it'd literally flatten anything on its surface. And if such a star had an atmosphere, it wouldn't spread up further than a foot or so above the surface. But if neutron stars are bizarre and spooky, magnetars are too, perhaps even more so. Thanks to their incredible magnetic pull, these stars would win in the strongest magnetic field competition, hands down. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. But that's not all. Even your molecules would change under the influence of the star's field. In the end, you'd kind of vanish. If a magnetar flew within 100,000 miles from our planet, it'd wipe out the data on every single credit card in the world. Astronomers have seen magnetars before, but they've never witnessed one getting born. After the light was first detected, scientists understood something didn't add up. They compared different kinds of observations. It turned out that the light spotted by the Hubble Space Telescope was 10 times brighter than predicted. This information made the scientists think outside the box. They realized an entirely new phenomenon was going on. The team had several ideas that could explain the bizarre brightness, but the most probable one was also the most eccentric. Before, scientists thought magnetars only appeared after massive stars exploded and left behind super-magnetized neutron stars. But now, they suppose a small number of magnetars may actually appear in a more peaceful way after two neutron stars merge. Scientists only know about no more than 10 magnetars in our home Milky Way galaxy. They don't know for sure what makes these stars so terrifyingly magnetic. Whatever it is, magnetars don't seem to last long. After 10,000 years or so, they return to a more familiar neutron star state. They're still extremely magnetic, super dense, but not so extreme. The closest magnetar people know about is 9,000 light-years away from Earth, in the constellation Carinae. Astronomers think the original star was 30 to 40 times the mass of the Sun, which is a really big one. Another magnetar is 18,000 light-years away from our planet. It suddenly started to burst in 2002. Around 80 bursts were recorded within a 4-hour window. After that, the magnetar has never been active again. By the way, the researchers were also immensely excited about seeing a kilonova. It occurred when the two neutron stars supposedly merged. A kilonova is more than 1,000 times brighter than a typical nova. Before, astronomers had only one confirmed and examined event of the kind. But the kilonova recorded in March looked different, and it might allow scientists to explore the diversity they knew nothing about.
Scientists have found an invisible star at the Milky Way center, a star that helped our galaxy be born. 26,000 light-years away, in the galactic center, a massive, invisible object started spreading everywhere, and you don't even know that you're breathing it right now. It all started in the 70s, when an astronomer named Vera Rubin was studying the Andromeda Galaxy. She decided to check whether stars move in a predictable way. Now let's say you're spinning a ball on a string around yourself. The closer the ball is to you, the faster it moves in a tight circle. But if you let the string out longer, the ball moves more slowly in a bigger loop. That's how gravity works. And the same goes for planets. The closer ones, like Mercury, zoom around quickly, completing their orbits in months. The far ones, like Neptune and Saturn, take their time, decades, to make one rotation. The stars themselves should orbit the centers of their galaxies the same way. The closer ones move fast, the farther ones are slower, right? But when Vera measured the speeds, she saw something impossible. They weren't slowing down. The faraway stars were moving just as fast as the ones near the center. By all logic, the galaxies should have torn themselves apart, but they didn't. And that meant something was holding them together, something undetectable. Some massive, invisible object in the galactic center warping reality without ever revealing itself. So she checked over and over with different galaxies. This wasn't a fluke, it was happening everywhere. Rubin had accidentally uncovered proof that galaxies were drowning in something far heavier than all the stars, planets, and gas in our entire universe combined. It was holding us with ghostly hands. Astronomers called it dark matter because it doesn't glow, doesn't reflect light, doesn't seem to interact with anything at all. It's just there. But all the calculations show us that it exists, and not merely exists, but makes up 85% of all the mass in the universe. We know that it sculpted galaxies. Without it, the world as we know it wouldn't exist. And yet, Just like with an invisible star scientists found at the Milky Way center, the only way to detect it was through gravity. So how do you find something that refuses to be found? Recently, scientists discovered there might be an invisible star at the Milky Way's center, and this fascinating discovery might finally help us understand what dark matter looks like. They began looking for dark matter's fingerprints, any signs of its presence anywhere. They studied how galaxies moved and smashed particles together in giant machines, hoping to create tiny bits of dark matter in the lab. This didn't really lead to anything. They didn't even know what to look for. Is dark matter even made of particles? There was a theory that suggested that it's made of ghostly particles that barely touch anything, or even weirder ones that might flicker in and out of existence in the blink of an eye. There was a problem, though. If dark matter really worked like that, then the centers of galaxies should be packed tight. Tons of matter would be crammed into a tiny space. But in our universe, galactic cores seem strangely soft, spread out, almost gentle. A new theory emerged, and it was wild. What if the dark matter at the heart of galaxies isn't made of heavy particles at all? What if it's made of something so delicate that it behaves more like a strand of hair? These hairs could be made of something incredibly light, lighter than anything we've ever seen, and billions of times smaller than a neutrino, which is already the lightest known particle. They called this idea fuzzy dark matter, and it might change everything we thought we knew about the universe. A team of astrophysicists wanted to test this idea, so they ran a simulation, creating a simple model of a galaxy with two main ingredients: a whole lot of fuzzy dark matter and a little bit of gas, the same kind of gas that forms the stars we can see. They pressed start and just let the system evolve by itself, watching how the two would interact. At first everything was pure chaos, but then the fuzzy dark matter started to gather. It pulled itself together, forming a massive invisible object near a galactic center. The gas followed, spreading throughout this ghostly mass, mixing with it and glowing faintly. And then it suddenly formed something incredible: dark stars. Not typical stars like our sun, blazing with heat and light. Instead, it's enormous, massive, invisible objects, a hybrid of two different kinds of matter. We've never seen anything like this before. An object that would stretch across thousands of light years, and yet they'd be almost weightless, more like cosmic puffy clouds than anything else. Scientists called them Fermion boson stars. Finally, this dark matter thing is starting to make sense. The core of this strange invisible star would have just the right density, not too dense, not too loose, and it looked exactly like what astronomers actually see in real galaxies. If it's confirmed, then it would finally explain how dark matter behaves and works. And if they're right, then every galaxy in the universe could be tied to one of those vast unseen giants. The Milky Way hidden star might be one of them, shaping our galaxy in ways we never realized. What's wild is that this stuff wouldn't behave like normal matter. It wouldn't form anything solid. Instead, it would be more like a complex, ever-moving web of filaments or hairs. This also means that Earth might be completely surrounded by it. Dark matter still follows the rules of gravity. As it moves past planets and stars, gravity pulls it into focused streams, so it's both hugging and passing through our planet, wobbling consistently. If we could see them, they might look like glowing invisible threads everywhere, and they'd pierce right through the planet, stretching far into space. But this is only the beginning. Now scientists need to refine their models, make them even more detailed, and compare their predictions to real galaxies. But this dark star discovery in the galaxy's center isn't our only clue. Luckily, the universe has given us a way to look for that fingerprint: gravitational lensing. When light from a faraway galaxy travels toward us, it sometimes passes by another massive galaxy on the way, or other massive objects with crazy gravity. Instead of continuing in a straight stream, light actually gets bent around the massive object because of that gravity. And when it finally reaches us, it creates a distorted and magnified version of the original galaxy. Basically, it's like looking through a piece of curved glass. If dark matter is fuzzy, then it should leave a strange pattern on these distorted images. Things should be a bit wavy and unclear. Scientists needed the perfect object to study this, and they found one. A faraway galaxy whose light was bent by gravity, creating a strange stretched-out image. They used super-powerful radio telescopes, connected them all over the world, and turned them into one giant telescope as big as the Earth itself. With this, they could zoom in so much that they could see details of that galaxy as tiny as a grain of sand on the moon. Then they ran a huge experiment. They created their own fake versions of this picture, simulations with various sizes of fuzzy dark matter particles. And at a certain point, they found the perfect match. This helped us calculate the exact mass of dark matter particles before we even detected them. And the clues are leading us right to our own galaxy. It seems like densest parts of these hairs, the roots, might be super close in the cosmic scale, just tens of thousands of miles from Earth. That's close enough for a space probe to reach. Now that scientists have found this invisible star at the Milky Way center, we just need to study it up close, send a mission to one of these roots, and then we might finally crack the greatest space mystery of all.
Spotted. It seems like two giant stars were caught in the middle of a romantic kiss. This sounds a little bit like paparazzi fodder at first, but we're actually talking about a cosmic twist an international team of astronomers has discovered. So, the life cycle of a solo star is relatively simple. They're born in vast, gassy areas of space, burn through their fuel, and at some moment, they explode as supernovae. But when stars are born relatively close to each other, their gravitational pull can cause them some troubles and captivate them into what seems like an eternal dance. In some moments, they come so close to each other that they're practically touching. These stars may spend billions of years circling each other, but their kiss lasts for a few million years only, which is just a blink of an eye in cosmic terms. The lead author of this study was on a mission to find these binary stars caught in such a cosmic kiss. He focused his search on the Tarantula Nebula, a beautiful star-forming region located in the Large Magellanic Cloud, which is 160,000 light-years away from our home planet. And there it was, the shiny double star system that stood out from the rest. The two stars found there were pretty big and nearly the same size. Together, they make a mass of about 57 times larger than that of our Sun. Before this, we discovered only 3 other binary systems with a large mass. And since these two stars were so close to each other, they created an intense gravitational pull. This made them orbit each other at a staggering rate of once a day, with their centers a mere 7.4 miles apart. With the stars being so close, they formed a bridge where their fuel could mingle, allowing for around 30% of their total volume to be shared between the two. Temperatures of this system were crazy too. At first, it seems the internal mixing of their energy might make these stars live longer, as it allows for more fuel to be burned and for longer periods of time. But this is just a temporary benefit. There are 2 most likely scenarios for the star's ultimate fate. They could merge to form one giant star, which would eventually explode into a supernova. Or they could each explode separately and live out their remaining years as black holes orbiting each other. If they merge, this process would probably take around 600,000 years, while if they become binary black holes, they could continue burning for another 3 million years. But both scenarios would ultimately lead to their destruction. Unless the stars could end up as 2 separate black holes drifting away from each other through the vastness of space, there's a possibility for that to happen too. There's something spectacular stargazers across the globe could see recently. Jupiter and Venus, the 2 brightest planets in the sky, ended up so close it appeared like they were about to collide, or as if they were kissing too. At least that's what it looked like from here on Earth.
In real terms, they're still 400 million miles away from each other. Here's another interesting thing astronomers like to talk about: G-objects. Those are celestial objects that look like clouds of dust and gas, but behave like stars. At the center of our galaxy, there's a supermassive black hole. It's 4 million times the mass of our Sun, and recently, scientists found out there are two mysterious G-objects that hang out pretty close to that black hole, so-called G1 and G2. And the most probable theory is that G2 are two stars that were orbiting the black hole in tandem and merged into an extremely large star cloaked in unusually thick gas and dust. During G2's closest approach to the black hole, it showed a strange signature. It was elongated, and much of its gas was torn apart. As it got closer to the black hole, it lost its outer shell, and now it's getting more compact again. The thing that has everyone excited about the G-objects is the material that gets pulled off of them by tidal forces as they sweep by the central black hole. This material must inevitably fall into the black hole, and the result is an impressive fireworks show. This happens because the material eaten by the black hole will heat up and emit radiation before it disappears across the event horizon. An event horizon is that scary boundary around a black hole from which nothing can escape. Now, it seems scientists have discovered 4 more G-objects, and they're all located within 0.13 light-years of this black hole. And it could be that all of the 6 objects used to be binary stars that got together and merged because of the powerful gravity of this giant black hole. Usually, it takes over 1 million years to finish the merging process between two stars. We definitely want more G-objects because it's one of the rare opportunities for us to study how things behave near a supermassive black hole without being swallowed. Yet. Have you heard of variable stars? Look up at the sky. We often think of the stars as unchanging, eternal lights. Yes, some stars might appear constant, but others change in brightness over time, which is why we call them variable stars. Some of them dim and brighten again over days, months, or even years. We can't see it with the naked eye. We're talking about changes astronomers can only notice using equipment and over longer periods. And how about vampire stars? Imagine 2 stars, a red giant and a white dwarf, in a binary system, swirling around each other like cosmic ballet dancers. The red giant, which used to be a vibrant and fiery star, now has aged and grown tired. Its outer layers of hydrogen, which were once held tightly by its gravity, have now weakened, making it vulnerable to the smaller, denser white dwarf. The white dwarf, known as the vampire star, thirsts for the hydrogen fuel that its larger sibling holds, and it sees a great chance there. As they spin together, the vampire star uses its powerful gravitational force to steal the hydrogen from the red giant's outer layers. The vampire star glows with a blue hue, looking full of energy and more youthful and vibrant than its aged dancing partner. Not only vampire stars, the horror continues with zombie stars too. Sometimes when the red giant explodes, it doesn't completely break up into smaller pieces. Instead, a white dwarf remnant is left behind. It's basically a zombie star that was gone at the moment, but has risen back to life. But this isn't your average zombie, hungry for brains. No, this star hungers for the very substance that its vampire sibling had been taking from it all along, hydrogen. And if the zombie star is close enough to its victim, it will start sucking material back in to start its core again. It will become a hydrogen explosive, ready to go boom in a spectacular show of cosmic revenge. It's a fascinating phenomenon. We usually won't even manage to detect it, because these explosions are much fainter than the usual supernovas. But when it does happen, the resulting blast is truly epic. And it destroys both the vampire star and its zombie sibling. It seems vampires and zombies may not be a work of fiction after all. Not only are we made of stardust, but we're also more similar to stars than we thought too. For example, stars also like to hang out with their close group of friends. Most stars prefer to travel through the universe in clusters. It's a group of stars that end up bound together by gravitational force. The stars in the cluster are mostly made of the same age and type, hobbies, and interests. I guess even they have better social lives than I do.
Saturn's iconic rings will disappear in less than 2 years. Soon, we won't be able to see Jupiter's Great Red Spot. Pluto's atmosphere might vanish any day now. Even the universe itself could be slowly evaporating right at this moment. But let me start from the very beginning. Saturn's rings won't vanish forever, at least in the near future, but they will seemingly disappear from view. This phenomenon is caused by the planet's tilt as it orbits the Sun. As a result, the eye-catching rings adorning the gas giant will get invisible to stargazers in 2025. This outrageous disappearance occurs because Saturn's thin rings turn edge-on. It's like holding a sheet of paper horizontally at eye level parallel to the ground so that only the edge of the paper can be seen. Something similar happens to the gas giant's rings. As the seasons on the planet progress, instead of the southern side of the rings tilted our way, we start seeing the northern side. But then the planet tilts again, revealing the southern side once again. Such a ring plane crossing happens every 15 years when our planet passes through the gas giant's ring plane. The last time this phenomenon occurred was in 2009. Afterward, the rings gradually became visible again over the course of several months. This time, the rings will be on edge in March 2025. Then they will slowly come back into view and disappear again in November of the same year. Soon after that, the rings will reappear, first becoming visible to the largest telescopes, later for everyone else to see. At the same time, further into the future, the rings might cease to exist for good. Astronomers have concluded that Saturn's rings, which mostly consist of ice and rocky dust from smashed asteroids, are younger than we thought. They're losing tons and tons of mass per second all the time, and it's likely to be a few 100 million years at most before they vanish completely. Let's move to the Great Red Spot on Jupiter. This immense raging storm might stop spinning in the next 20 years. The storm in question is larger than our planet. It was first spotted in 1830, but observations from the 1600s mention the presence of a giant spot on Jupiter too. If it was the same Great Red Spot, then we can say that the storm has been raging for centuries. The storm's vortex has remained so powerful thanks to Jupiter's 300 to 400 mile-per-hour jet streams. But like any other storm, the Great Red can't keep raging forever. It's been shrinking for a long time. In a decade or two, it's predicted to turn into GRC, the Great Red Circle, and who knows, maybe it will later turn into the GRM, the Great Red Memory. In the late 1800s, the storm was more than 35,000 miles across, 4 times the diameter of Earth. But when Voyager 2 flew past Jupiter in 1979, the storm had already shrunk almost twice its original size, and this shrinking is still happening. In 2017, the GRS spanned the width of a bit more than 10,150 miles, less than 1.3 times the diameter of Earth. Moving on, Pluto's atmosphere is going through a weird transformation. This icy dwarf planet sitting over 3 billion miles away from Earth in the region of the Kuiper Belt drew astronomers' attention in 2018 when it passed in front of a star. With such a powerful source of light illuminating Pluto, researchers managed to examine the dwarf planet and its atmosphere. They came to a shocking conclusion that Pluto's atmosphere is refreezing back onto its surface as the dwarf planet gets colder and colder. Astronomers used several telescopes in different spots in the USA and Mexico to observe Pluto and its thin atmosphere, which is mainly made of nitrogen. This atmosphere is supported by the vapor pressure of ice on the surface of the dwarf planet. For around 25 years, Pluto has been moving further away from the Sun, and its surface temperature has been gradually going down. Pluto is really far from our star at the moment. But at one point, it will start getting closer in other regions of its incredibly huge orbit. Besides Jupiter's Great Red Spot, Saturn's rings, and Pluto's atmosphere, we're also losing stars. But stars don't vanish, right? For thousands of years, scientists believed that lights in the sky were fixed and unchanging. Even after they realized those lights were physical objects, just like the sun, they were still sure that stars went through major changes extremely slowly, on timescales of millions and billions of years. In reality, though, the most massive stars, which can be hundreds of times heavier than the sun, can go through sudden catastrophic events. For example, once they reach the ends of their lives, they pass away in blinding explosions of supernovae, shining for months on end and visible across hundreds of millions of light years. But there are stars that seem to just wink out of visibility. It should be impossible. And over the past years, a group of researchers tried to figure out whether there's actually a chance of such a phenomenon happening. They started to compare data collected over decades of observations. The project is called VASCO, the Vanishing and Appearing Sources During a Century of Observations. The scientists are interested in all kinds of disappearing objects, but they're hoping to find a star that was steady and present for a long time, and then just vanished without a trace. Even if you point a super powerful telescope there, you'll still see nothing. Our current understanding of space and its laws suggest that stars change very slowly over long periods of time. Dramatic disappearances are supposed to leave noticeable traces behind. Of course, it doesn't mean that all stars should shine steadily. The sky is filled with stars that change in brightness and pulsate. But VASCO is about something very different. They want to find something that goes from a completely steady star to vanishing entirely. Such a phenomenon hasn't been documented yet, and such a discovery might lead to new physics. And now, let's move on to the most disturbing part, the one about the evaporating universe. According to a famous theory proposed by Stephen Hawking, black holes, the densest objects in the universe, evaporate over time. They lose mass in the form of bizarre radiation. But a new study claims that Hawking radiation, or something very similar to it, might not be limited to black holes. It's likely to be everywhere, and it could mean that the universe is slowly but surely evaporating right in front of our eyes. Now, Hawking radiation is something no one has ever observed, but theories and experiments suggest that it can actually exist. Let's see how it works. There's a misconception that black holes are cosmic hoovers, slurping up everything that comes too close with the help of their immense gravitational pull. In reality, though, black holes don't have more gravity than any other body of a similar mass. What they're famous for is their density, incredible amounts of mass packed into a tiny, tiny space. Within a certain proximity to such a dense object, gravitational pull becomes so powerful that it becomes impossible to escape. Not even the speed of light in a vacuum is enough, and that's the fastest known thing in the universe. At the same time, anything massive or dense enough can produce a serious curvature of space-time. In simple words, the immense gravitational field of these objects makes space-time wrap around them. Even though black holes are the most extreme example, space-time also curves around other super-dense objects, like white dwarfs, and neutron stars or galaxy clusters. It means that any super-dense and supermassive object can have some sort of radiation similar to Hawking radiation. And after a very, very long period of time, it could lead to everything in the universe evaporating, following the fate of old supermassive black holes. If it turns out to be true, it will change our understanding not only of Hawking radiation, but also our view of the universe and its and our future. Locating the North Star is quite easy on a clear night. The only thing you need to do is find the Big Dipper. Those two stars on the end of the Dipper's cup point the way to the North Star. See? It's the tip of the handle of the Little Dipper, or the tail of the Little Bear. It's in the constellation Ursa Minor, over there. People have been watching the North Star for centuries. This bright star is also known as Polaris. It's situated almost directly over our planet's North Pole, which makes it a great landmark for a traveler without a compass, or a GPS on their smartphone. It's also Earth's closest Cepheid. That's what we call a star that pulses regularly in brightness and diameter. Polaris is also part of a binary system of 2 stars. It's got a dimmer sister. It's known as Polaris B. You can actually see it circling the North Stars from Earth. But the more astronomers watch Polaris, the less they understand. The problem is, no one can agree on how big or distant the star is. Scientists have several ways to estimate the mass, age, and distance of a star like Polaris. One method is called the stellar evolution method. After studying the brightness, color, and rate of pulsation of a star, experts use this data to figure out how big or bright it is, as well as what stage of life it's in. Once these details are clear, it's not hard to find out how far a star actually is. It's simple math once you know the luminosity of a star in real life and how dim it looks from our planet. Such models are especially precise for stars like Polaris because the rate of their pulsing is directly related to their brightness. This makes it easy to figure out the distance to any of those stars. Astronomers trust this method so much that Cepheids have become an important tool for measuring distances all across the universe. At the same time, there are other ways to study the North Star, and they don't agree with the stellar evolution models. Polaris is a so-called astrometric binary. It means you can see its companion going around it. It looks as if a circle is being drawn around the bigger star. To complete one orbit, the smaller star needs around 26 years. Even though astronomers haven't made detailed observations of Polaris B's full circuit, they've seen enough to know what its orbit looks like. Using this information, one can apply Newton's laws of gravity to calculate the masses of the 2 stars. Combined with the Hubble Space Telescope's new measurements, these calculations lead to very precise numbers. Polaris is supposed to be around 3.45 times the mass of the Sun, but that's much less than the mass you get from stellar evolution models. They suggest a value of almost 7 times the mass of the Sun. But there's another reason why this star system is weird. After calculating the ages of the stars, researchers concluded that Polaris B is much older than its bigger sibling, but it's extremely unusual for a binary system. Normally, both stars are of the same age. One explanation might be that at least one of the measurements is simply wrong. After all, Polaris is a difficult star to study. Since it's positioned above our planet's North Pole, it's outside the field of view of most telescopes. As for those telescopes that do have the needed equipment for measuring the star's properties precisely, they're typically used for studying much more distant and fainter stars. Polaris is simply too bright for such instruments. It blinds them. There's a theory that the main star of the Polaris system was once 2 stars, but they collided a few million years ago. Such a binary collision could rejuvenate stars by pulling in extra material and making the stars look as if they went through the fountain of youth. It would also explain some other oddities, since stars that appear as a result of binary collisions don't fit stellar evolution models. Unfortunately, so far, none of the theories have been confirmed. The North Star is actually a big deal. Earth is spinning non-stop, which causes the sun to rise and set and stars to travel across the sky. Our planet is also tilted. That's why we have seasons. If we drew a line through the axis Earth spins around and extended it over 300 light-years past the North Pole, at the end of that imaginary line, there would be the North Star. It stays almost exactly at the same spot in the sky at all times and always points the way north. It's really important for navigation. People heavily relied on it in the days before GPS. If you were standing on the equator, Polaris would be right at the horizon. At the North Pole, it would seem to be right over your head. In other words, using the star's height in the sky, you can not only figure out the needed direction, but also understand where you are on Earth. Curiously, there's no South Star. There isn't a bright enough star right above the South Pole, but one day we might get such a star. When you spin a top on the table, its end moves in a circle. We know this phenomenon as precession. Earth behaves in the same way, and the North and South Poles won't always point towards the same spots in the sky. In the next 26,000 years, it may cause the North Star to change from Polaris to a few other stars, and back again. One day, the title of the North Star will go to Vega. It's the 5th brightest star in the night sky and the 2nd brightest in the northern celestial hemisphere. Vega has another name, Alpha Lyrae. That's because it's the main star of the Lyra constellation. Vega has been one of the most crucial stars to people since ancient times. It's very bright and blue, hence very recognizable. Vega was the North Star several thousand years ago, and it'll regain this status in 12,000 years or so. This star is located a mere 25 light-years from Earth. It's just 450 million years old, which makes it way younger than our own 4.6 billion-year-old star system. Astronomers study Vega to learn more about star systems in the early stages of their formation. Vega is almost directly overhead at mid-northern latitudes on a summer night. It hides behind the horizon for only 7 hours a day. You can see it on any night of the year. If you travel farther south, you'll find out that Vega lies below the horizon for longer periods of time. But in Alaska, northern Canada, and some parts of Europe, Vega never sets. Vega's blue-white light is bright enough to be featured a lot in ancient cultures, from the Chinese to the Polynesians to the Hindus. Vega's name can also be translated as falling or swooping. This is a reference to the times when people regarded this constellation as a swooping vulture, not a lyre. Vega was also the first star to get photographed, other than the Sun, of course. To do it, astronomers at Harvard College Observatory used a 15-inch refractor, and it happened again in 1850. Around 2 decades later, an amateur astronomer broke down Vega's light to reveal various elements making up the star. In 2006, thanks to telescopic observations, scientists found out that Vega was whipping around so fast that its poles were several thousand degrees warmer than its equator. The star rotates every 12.5 hours and is at 90% of its critical rotation speed. That's the velocity at which an object can tear itself apart. In 2013, researchers announced that they had discovered an asteroid belt around Vega. It means there might be planets somewhere out there among space rocks. There are 2 areas, an outer region that contains icy asteroids and an inner region with warmer space rocks. Scientists can examine bright stars like Vega using NASA's mission called TESS, which stands for Transiting Exoplanet Survey Satellite. It was launched in 2018 to conduct an all-sky survey. The main goal of this mission is to search for exoplanets, but the satellite can also look for star variability. By examining such stars as Vega, TESS can help scientists learn more about the early stages of star evolution.
Right after its creation, the cosmos was shrouded in darkness. I mean, I wasn't there, but that's what most scientists are thinking. All of the stars were hidden behind a thick cloud of primordial gases. Then, all of a sudden, something cleared up this fog, and the universe started shining as it finally woke up. But how did this happen? 8 faint, recently discovered galaxies might hold the answer. The Big Bang created our world around 13.8 billion years ago. At first, it was just a super hot and chaotic boiling soup of particles. But over time, things cooled down, and particles could finally stick to each other. That's how the atoms appeared. Some helium, but mostly hydrogen, the very first element. And these first elements started creating thick gas clouds, which were very opaque. Then the first stars started forming. They were incredibly bright, emitting lots of light, including ultraviolet radiation. But even though these stars were shining, much of their light couldn't travel far because of that nasty hydrogen fog. The gas clouds absorbed and scattered any little light particles around. It was like the light was trapped around the stars. The Dark Ages lasted for hundreds of millions of years. Then, everything changed. Recently, the James Webb Space Telescope has spotted ancient dwarf galaxies from that epoch. Turns out, they're the ones we should be thanking for lighting up the universe. Back then, they were filled with early stars. These stars emitted tons of radiation that was so powerful that it managed not to just overcome, but break apart the hydrogen atoms in the fog. It turned them into charged particles, like particles that carry a little bit of electricity called ions. Little by little, the fog was cleared away. This process of clearing out the fog is called reionization, and this beautiful time is known as the epoch of reionization. Finally, the light was able to travel to all corners of the universe, which was a game changer, just like humans' Age of Enlightenment. To find these little igniters, astronomers used a technique called gravitational lensing. Imagine light traveling through space like a straight beam. But just like everything in our world, even time, light obeys gravity. If it's too strong, it'll literally bend the light beams. So when the beams pass near a massive object, the object's gravity pulls on them, curling and twisting their path. That's why black holes look so creepy, as they stretch stars and space around them like some whirlpools. But it's not that creepy. A regular glass or magnifying glass does something similar, hence the name gravitational lensing. When the lensing object is horrifyingly massive, it bends the light into multiple images of the same object, creating a creepy and mesmerizing structure called an Einstein ring. But if it's not that big, then the bending is less dramatic, and it just slightly distorts the shape of the background object, making it look kinda stretched. Gravitational lensing also helps scientists study things like the spooky dark matter. If the light looks stretched, and it's not just because of some obvious massive objects nearby, then it might be something invisible and heavy bending it. Since these 8 galaxies were too faint, no wonder they're almost as old as my unread emails. Scientists had to use these gravity tricks to observe them. The team studied light from galaxies that are over 13 billion years old. Finally, they focused on a galaxy cluster called Abell 2744, also known as Pandora's Cluster. And these findings helped them understand how even little fellas played a huge role in transforming the early universe. The James Webb Telescope is an incredible tool, and soon it might help us look at even earlier times, at the cosmic dawn, when the universe was only several millions of years old. Another great tool, called the Roman Space Telescope, is going to help it. It's also possible that these galaxies weren't the only helpers in this entire saga. These early massive stars were absolutely terrifying. They just don't make them like that anymore. Some estimates suggest they were 30 to 300 times more massive than our Sun, and millions of times brighter. Modern stars have some heavier elements in them, but back then, they used only the stuff available, hydrogen and helium, which is why they were so hot and shiny. But they also had very short lifespans, lasting just a few million years. For example, our Sun is 4.6 billion years old and is still going strong, thankfully. At the end of their lives, they went supernova. These colorful bursts of energy were so strong that they forged the first heavier elements in our world and spread them across the universe, planting first seeds for the future planets. Meanwhile, the stars themselves didn't just disappear. They collapsed under their own gravity, creating the first black holes. Now, the black holes are also known for producing insane amounts of radiation, so it's possible that they might have helped speed up the clearing of the fog. Ironically, they help the universe shine brighter while sucking up the light at the same time. Recent discoveries show that black holes might be much older than we used to believe. They probably helped new stars and galaxies form. They were millions or even billions of times the mass of the Sun. The James Webb Telescope has already found a pair of early quasars. That's what we call the bright centers of galaxies powered by supermassive black holes. It's a curious pair of quasars that are merging just 900 million years after the Big Bang. This might be the earliest and most distant pair of merging quasars ever found. The telescope has also been studying things that are called cosmic lighthouses. In scientific language, they're pulsars. Pulsars are super-dense remnants of massive stars. They form from stars that were once 4 to 8 times more massive than our Sun. One of the greatest things about them is how fast they spin. They're one of the fastest objects in the universe. They might do around 700 rotations in just 1 second. They got their name because they behave like lighthouses, basically flickering radio waves. These beams of radiation sweep across the sky, creating a pulse-like signal that we detect. Now, a star basically works like this. There's nuclear fusion happening inside of its core. Atoms get fused in each other, move at crazy speeds, bump, all meanwhile releasing an unbelievable amount of energy. That's why they emit tons of light and heat. Of course, all this pressure tries to push outward, sweating like crazy to expand a star. The greatest the fusion is, the more powerful and insane the star gets. On the other hand, there's gravity that's pulling inward, trying to compress the star and keep it a nice small dense ball. As long as there's balance, the star keeps living, but when it gets old and spends all of its nuclear fuel, it becomes too weak to generate the energy it needs and can't fight against gravity anymore. That's when it basically collapses under its own weight, going supernova. What's left behind is the star's core, but now it's crushed down to an incredibly small size, about 12 to 17 miles across. It's roughly the size of a city. This dense core is known as a neutron star. The material in a neutron star is so dense that just a teaspoon of it would weigh as much as 4 billion tons, like 10,000 Empire State Buildings. And all this collapse sets off a trigger, causing the neutron star to spin super fast, creating a pulsar. It's kind of like when an ice skater spins faster when they pull their arms in. Pulsars often have a smaller star friend orbiting them, although it's not always a friendly relationship. Not long ago, astronomers discovered a pulsar that was surrounded by lots of energetic material for some reason. They realized that all this material was the remnants of another much larger star. Turns out, the pulsar had been slowly destroying its friend with its terrifying radiation and particles until it basically ate the neighbor away. It's similar to how a black widow spider consumes its mate. So, systems like this were called black widow pulsars. In any case, these lighthouses most likely help the reionization process as well. A long time ago, they could be very energetic stars in small galaxies and could emit enough radiation to transform the early universe. The James Webb Telescope's mission is to find more of these lighthouses and see what role they played in the universe's evolution.
A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Astronomers examined the phenomenon with X-ray, radio, optical, and infrared waves. It turned out that people had finally seen a newborn magnetar for the first time ever. It was likely formed after two neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22, 2020. Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of its nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. If not, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our sun is almost 865,000 miles across, which is 109 Earths put side by side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. It's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's a rare form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. Even your molecules would change under the influence of the star's field. In the end, you'd pretty much vanish. If a magnetar flew within 100,000 miles from our planet, it would wipe out all the data on every single credit card in the world.
Check out this interstellar showstopper. Shadows doing a little dance in space have spilled the beans on a mind-boggling secret about our solar system's origins. There's a star called TW Hydrae that's playing host to some mischievous disks that are out of sync, spinning at slightly wonky angles. But what's causing this celestial chaos? Well, it seems like a bunch of baby planets are misbehaving, tugging at the disks with their gravity and throwing everything off balance. Hold on tight, because things are about to get even more interesting. This star is a real newbie in the cosmic neighborhood at just 8 million years old. Yep, that's practically a cosmic toddler compared to the ancient sun, which has been around for a whopping 4.6 billion years. This new start hasn't even started its hydrogen-burning season yet. It's still in the process of growing and compacting under its own gravitational pull. Think of it as the sun's younger doppelganger. Here's the lowdown on how stars like TW Hydrae get their groove on. They gather cosmic dust and gas from their surroundings, which forms a swirling disk around them. This disk is like a cosmic buffet for planet formation. Little specks of matter come together, forming bigger and bigger clumps that eventually collide and grow into full-fledged planets. Since they're born from a flat disk, these planets usually end up orbiting their star in a neat, flat plane. Now, our new star has struck gold with its unique orientation. We're lucky enough to have a front-row seat to this cosmic construction site because we can see the disk face on. And guess what? It looks a lot like our solar system. This gives us a chance to uncover some juicy secrets about our own planetary origins. Back in 2017, eagle-eyed astronomers noticed a shadow making its way around this new star's disk. It completed a full rotation every 16 years. Initially, they thought this shadow might be evidence of a sneaky young planet forming within the disk, causing parts of it to wobble in different directions. Fast forward to 2021, and things took an unexpected twist. The shadow did something totally unexpected, leaving everyone scratching their heads. Hold your horses, though. The savvy team of astronomers didn't give up easily. They put their thinking caps on and came up with a few possible explanations. After extensive modeling, they hit the jackpot. It turns out not just one, but two wobbly disks were at play, casting shadows on a third outer disk. This suggests the existence of a second young planet, making it a cosmic double feature. Imagine these two planets zooming around, one trying to outpace the other, like a pair of racing cars. The data suggests that the first disk is about 5 to 6 astronomical units from the star, while the second disk is around 6 to 7 astronomical units away. For reference, our mighty Jupiter orbits the Sun at a distance of 5.2 astronomical units. So, it's like a cosmic game of tag with the planets influencing each other's orbits. As these planetary misfits go about their orbits, their gravitational interplay causes the disks to tilt slightly with respect to one another. This creates shadows that dim the outer regions of the disk. Oh, and by the way, this totally matches our own solar system vibe. Why? Because some of the planets in our own solar system are rebels too, and have orbital inclinations that vary by up to 7 degrees. I'm looking at you, Mercury. Or a whopping 17 degrees if you count our dear friend Pluto. Who knows? If we continue researching this new star, it might just spill the beans on how our own solar system's got its funky orbital inclinations. How exactly do we define our solar system, though? It's like a celestial neighborhood with 8 funky planets happily orbiting our sun. In order of proximity to the sun, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Oh, and we can't forget Pluto, our little dwarf planet friend who used to be part of the Planet Club. Our solar system is way more than just the sum of its planets. It's like a fantastical mashup of asteroids, comets, stars, moons, and a whole bunch of other spacey stuff that makes our cosmic home truly enchanting. Contrary to popular belief, the hottest planet isn't the one getting all cozy next to the sun. Nope. It's Venus, the second closest planet. How come, you might ask? Well, Venus is scorching because it has an ultra-thick atmosphere. It's basically like it's wearing 100 layers of sweaters. When sunlight pierces through this super dense atmosphere, it turns Venus into a fiery furnace. We've also got some rocks on Earth that are like interplanetary tourists from Mars. Can you believe it? Scientists have found these rocks here, and they're chock full of the same gassy goodness found on the red planet. How did they get here? The most plausible scenario is that Mars sent a souvenir package through an asteroid crash or volcanic fireworks show. Our planet is also the ultimate chemistry whiz. Sure, other planets have bits and pieces of the elements we have, but we've got the whole shebang. Iron, oxygen, silicon, sulfur, magnesium, sodium, nickel, calcium, aluminum, if you can name it, we most likely have it here somewhere. Other planets are like, hey, we're mostly rock with helium and hydrogen, but we're here with our unique blend of interstellar awesomeness. Jupiter, however, the heavyweight champ of our solar system, has a never-ending party happening in its atmosphere. It's called the Great Red Spot, and it's been swirling with hurricane-like intensity for more than 300 years. This stormy event boasts extremely powerful winds, reaching a blazing 270 miles per hour. Oh, and by the way, this colossal storm is more than twice the size of our entire Earth. Neptune, on the other hand, knows how to make an entrance. It's got the fastest wind speeds in the solar system, zipping around at more than 1,200 miles per hour. Just like Jupiter and Saturn, Neptune actually produces more energy than it gets from the sun. As it turns out, Neptune's energy comes from its core, and that's what powers its super-duper strong winds on the surface. Now you might be wondering, how does Neptune manage to keep all that energy to itself? Well, it's all thanks to a special blanket of methane gas, which acts like a cosmic snuggie. This snuggie, or rather greenhouse gas, traps the heat and keeps it cozy on the planet. If Neptune were a bit more like Uranus, which is a bit of a slacker in the energy department, all that heat would have gone on a space vacation ages ago. Despite the chilly temperatures, Neptune doesn't let it bring down its funky style. It radiates a whopping 2.7 times more heat than it receives from the sun. It's like Neptune saying, hey sun, you're cool, but I've got enough heat to make my winds wild and crazy. Space isn't as far away as you might imagine. The Kármán line, which is approximately 62 miles above Earth, is like the official starting point of space. If you could drive your car straight up into the sky, you'd actually reach that mark in less than an hour. That's even quicker than some people's daily commute. As it turns out, our solar system is actually already halfway through its estimated life cycle. Scientists estimate that our solar system is around 4.6 billion years old, and it's expected to keep going strong for another 5 billion years. We've still got a lot of time left in this celestial ride. In the meantime, the sun, our fiery superstar, will keep trying to pull the planets towards it. Talk about being clingy. Gravity on the sun is so powerful that it's constantly exerting its pull. But don't worry, the planets are not just passive participants. They're like determined tug-of-war players, pulling in the opposite direction and keeping a fine balance. As a result, the planets end up kind of floating in the middle. It's no wonder the sun has so much power around here. The mass of the sun is mind-blowingly huge. In fact, the sun's mass is around 330,000 times that of our beloved Earth, and get this, it accounts for over 99% of the total mass in our solar system.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Betelgeuse, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Betelgeuse. It's one of the brightest stars we can see from Earth, and it's just 640 light-years away. No big deal. Betelgeuse has a blue-white O-type star, which is one of the hottest types to exist. Betelgeuse was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Betelgeuse. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Betelgeuse replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Betelgeuse spinning way faster than it should for a star of its size. Huge stars like Betelgeuse are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Betelgeuse's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our Sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the Sun, but Earth's entire orbit around the Sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Betelgeuse might have less than 300 years of fuel left in its core. They say that Betelgeuse is known to expand and contract regularly, and its pulsation pattern hints that Betelgeuse is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Betelgeuse, and it's been dimming steadily over the past century, unlike the relatively stable Betelgeuse. If Betelgeuse was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Betelgeuse as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Betelgeuse won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm. Locating the North Star is quite easy on a clear night. The only thing you need to do is find the Big Dipper. Those 2 stars on the end of the Dipper's cup point the way to the North Star. See? It's the tip of the handle of the Little Dipper, or the tail of the Little Bear. It's in the constellation Ursa Minor, over there. People have been watching the North Star for centuries. This bright star is also known as Polaris. It's situated almost directly over our planet's North Pole, which makes it a great landmark for a traveler without a compass, or a GPS on their smartphone. It's also Earth's closest Cepheid. That's what we call a star that pulses regularly in brightness and diameter. Polaris is also part of a binary system of 2 stars. It's got a dimmer sister. It's known as Polaris B. You can actually see it circling the North Stars from Earth. But the more astronomers watch Polaris, the less they understand. The problem is, no one can agree on how big or distant the star is. Scientists have several ways to estimate the mass, age, and distance of a star like Polaris. One method is called the stellar evolution method. After studying the brightness, color, and rate of pulsation of a star, experts use this data to figure out how big or bright it is, as well as what stage of life it's in. Once these details are clear, it's not hard to find out how far a star actually is. It's simple math once you know the luminosity of a star in real life and how dim it looks from our planet. Such models are especially precise for stars like Polaris because the rate of their pulsing is directly related to their brightness. This makes it easy to figure out the distance to any of those stars. Astronomers trust this method so much that Cepheids have become an important tool for measuring distances all across the universe. At the same time, there are other ways to study the North Star, and they don't agree with the stellar evolution models. Polaris is a so-called astrometric binary. It means you can see its companion going around it. It looks as if a circle is being drawn around the bigger star. To complete one orbit, the smaller star needs around 26 years. Even though astronomers haven't made detailed observations of Polaris B's full circuit, they've seen enough to know what its orbit looks like. Using this information, one can apply Newton's laws of gravity to calculate the masses of the two stars. Combined with the Hubble Space Telescope's new measurements, these calculations lead to very precise numbers. Polaris is supposed to be around 3.45 times the mass of the Sun, but that's much less than the mass you get from stellar evolution models. They suggest a value of almost 7 times the mass of the Sun. But there's another reason why this star system is weird. After calculating the ages of the stars, researchers concluded that Polaris B is much older than its bigger sibling, but it's extremely unusual for a binary system. Normally, both stars are of the same age. One explanation might be that at least one of the measurements is simply wrong. After all, Polaris is a difficult star to study. Since it's positioned above our planet's North Pole, it's outside the field of view of most telescopes. As for those telescopes that do have the needed equipment for measuring the star's properties precisely, they're typically used for studying much more distant and fainter stars. Polaris is simply too bright for such instruments. It blinds them. There's a theory that the main star of the Polaris system was once two stars, but they collided a few million years ago. Such a binary collision could rejuvenate stars by pulling in extra material and making the stars look as if they went through the fountain of youth. It would also explain some other oddities, since stars that appear as a result of binary collisions don't fit stellar evolution models. Unfortunately, so far, none of the theories have been confirmed. The North Star is actually a big deal. Earth is spinning non-stop, which causes the sun to rise and set and stars to travel across the sky. Our planet is also tilted. That's why we have seasons. If we drew a line through the axis Earth spins around and extended it over 300 light-years past the North Pole, at the end of that imaginary line, there would be the North Star. It stays almost exactly at the same spot in the sky at all times, and always points the way north. It's really important for navigation. People heavily relied on it in the days before GPS. If you were standing on the equator, Polaris would be right at the horizon. At the North Pole, it would seem to be right over your head. In other words, using the star's height in the sky, you can not only figure out the needed direction, but also understand where you are on Earth. Curiously, there's no South Star. There isn't a bright enough star right above the South Pole, but one day we might get such a star. When you spin a top on the table, its end moves in a circle. We know this phenomenon as precession. Earth behaves in the same way, and the North and South poles won't always point towards the same spots in the sky. In the next 26,000 years, it may cause the North Star to change from Polaris to a few other stars and back again. One day, the title of the North Star will go to Vega. It's the 5th brightest star in the night sky and the 2nd brightest in the northern celestial hemisphere. Vega has another name, Alpha Lyrae. That's because it's the main star of the Lyra constellation. Vega has been one of the most crucial stars to people since ancient times. It's very bright and blue, hence very recognizable. Vega was the North Star several thousand years ago, and it'll regain this status in 12,000 years or so. This star is located a mere 25 light-years from Earth. It's just 450 million years old, which makes it way younger than our own 4.6 billion-year-old star system. Astronomers study Vega to learn more about star systems in the early stages of their formation. Vega is almost directly overhead at mid-northern latitudes on a summer night. It hides behind the horizon for only 7 hours a day. You can see it on any night of the year. If you travel farther south, you'll find out that Vega lies below the horizon for longer periods of time. But in Alaska, northern Canada, and some parts of Europe, Vega never sets. Vega's blue-white light is bright enough to be featured a lot in ancient cultures, from the Chinese to the Polynesians to the Hindus. Vega's name can also be translated as falling or swooping. This is a reference to the times when people regarded this constellation as a swooping vulture, not a Lyre. Vega was also the first star to get photographed, other than the Sun, of course. To do it, astronomers at Harvard College Observatory used a 15-inch refractor, and it happened again in 1850. Around 2 decades later, an amateur astronomer broke down Vega's light to reveal various elements making up the star. In 2006, thanks to telescopic observations, scientists found out that Vega was whipping around so fast that its poles were several thousand degrees warmer than its equator. The star rotates every 12.5 hours and is at 90% of its critical rotation speed. That's the velocity at which an object can tear itself apart. In 2013, researchers announced that they had discovered an asteroid belt around Vega. It means there might be planets somewhere out there among space rocks. There are 2 areas, an outer region that contains icy asteroids and an inner region with warmer space rocks. Scientists can examine bright stars like Vega using NASA's mission called TESS, which stands for Transiting Exoplanet Survey Satellite. It was launched in 2018 to conduct an all-sky survey. The main goal of this mission is to search for exoplanets, but the satellite can also look for star variability. By examining such stars as Vega, TESS can help scientists learn more about the early stages of star evolution.
Hey Mythbusters! Today we're debunking some classic space myths. Hop on the next space shuttle and let's get to the bottom of these tales once and for all. Picture this. You're floating weightlessly in space, sipping on a cup of delicious hot chocolate, when a peculiar thought pops into your head. Can you scream in outer space? And if yes, would anyone hear that scream?
If you've watched the movie Alien, then you know the answer to this one. You can't hear sounds in outer space.
It's not that sounds don't exist. It's just that you can't hear them. There's no one better to clarify this myth than Chris Hadfield. He's been on a couple of spacewalks during his life as an astronaut. And once you're out there in the darkness of space, you can't hear anything.
All you hear is silence. Complete silence.
But hey, just around the corner is a massive ball of explosion, aka the sun. We just can't hear the explosions happening because there's no medium for sound to travel through. It would be quite uncomfortable for an astronaut, though, if they could hear all the noises going on in outer space. Now, imagine you're zipping through space, feeling like a futuristic superhero, when a shooting star passes by your side. But wait, is it really a star? Unfortunately, shooting stars are not stars at all. They are small space rocks known as meteoroids, entering Earth's atmosphere and creating a stunning light show. Oh, and since we're debunking myths, let's head straight for another one. You've probably heard that meteors only crash into Earth on extremely rare occasions, like once every dinosaur extinguishing apocalypse. That's not true. Scientists estimate that about 48 tons of meteoritic material fall on Earth each day. But almost all of this material is vaporized in Earth's atmosphere. The bright trail we see in the night sky is what we popularly call a shooting star. Next time you make a wish upon a shooting star, remember, you're actually hoping on a tiny piece of space debris. It's not so romantic after all. Can we or can we not fly into the stratosphere on air balloons? Apparently, we can. The Earth's stratosphere starts relatively close to the ground, about 7 or 8 miles up from the Earth's surface, but it continues a long way up. If you were to fly yourself all the way into the stratosphere with some type of air balloon, just make sure you have really good equipment at hand. You'll need a special suit and some breathing devices because air starts to get pretty thin the higher you get. Of course, if you do go all the way up, you need to get a picture of the Earth's curvature. So take a chest harness with you where you can put a special camera or something like that. And how about you live stream the whole thing? That would be a first! Imagine it's been 102 days since you left Earth. You've adapted well to life in outer space, but something weird is happening to your body. You're getting taller. How is that even possible? Don't stress about it, it's completely normal. The truth of the matter is, you're not getting taller. This is what happens to your body when it's not under the effect of gravity. Our body has natural space between vertebrae and joints. On Earth, this space is almost completely squeezed due to the force of gravity. But in space, your body gets some time off of the pushing force of gravity and begins to stretch more and more. So yes, astronauts can grow up to 3% taller when they're on long missions. And here's a curiosity, NASA has that all covered when they're tailor-making spacesuits, of course. This way, astronauts will always have extra space in their suits. Once astronauts are back on Earth, the anti-gravity effect will wear off. So maybe they'll spend a few days wearing capri pants before it fits perfectly on their bodies again. Never have I ever pictured an airplane door bursting open mid-flight and a bunch of passengers being sucked into the atmosphere like flying feathers. Well, I'm betting most of you have had similar thoughts when getting inside a plane. Now imagine if this were to happen in outer space. Common knowledge says that if an astronaut is sucked out of an airlock, this person would be burnt to a crisp. Brace yourselves, because this is not only true, but the reality of it is way worse. According to astronaut Chris Hadfield, this is what would happen. The part of your body in the shade of the sun would experience temperatures of negative 418 degrees Fahrenheit, while the part of you getting sunlight would burn at around 480 degrees Fahrenheit. Your lungs would collapse, and your blood would start to boil like tea water. So you would burn, freeze, lose your ability to breathe, and boil. Yikes! How many times have you heard that astronauts have to work out every second of every day, otherwise they'll pass out? This is a complete myth. Remember we talked about gravity earlier? Due to the lack of gravity in outer space, our bodies don't have to do any heavy work. Our torsos don't have to sustain the weight of our heads, and we don't have to make any effort to move our legs because, essentially, there's no walking in outer space. Now imagine living like that for 6 months, or even a year of your life. Your muscles could turn into jello. That's why astronauts work out. They'll strap themselves and run on a treadmill, or they'll do some weightlifting in a special machine. This way, their muscles won't feel the lack of gravity too much. They do need to keep hydrated though. You know what? If I was an astronaut, I'd ask NASA if I could take my super soft water flask up into space with me. You've probably heard that space smells like burnt steak or barbecue sauce. Now, as much as this sounds absurd, this myth is more true than it is false. Astronauts obviously can't smell space when they're in it because they can't take off their helmets. They usually smell it once a space vehicle docks and they open up a hatch. Apparently, what causes this smell is the presence of hydrocarbons that float around in space. Who would have thought, huh? Hey smart people, let me ask you a question. Do you really think that if astronauts fly at the speed of light, they won't age a single second? I knew you'd say no. Let's get a few things straight. First of all, we haven't figured out how to operate vehicles at the speed of light. This would require an immense amount of energy, and we don't have the technology to do that. Second, even if we managed to send a human inside a spacecraft that traveled at the speed of light, this person would still age. They would age differently than the people who remained on Earth, that's a fact, but they would still age. Do you lot really think there's such a thing as immortality? Nah. If you've seen the first Avatar, then you certainly remember that humans only managed to get to Pandora because they traveled in Cryosleep. In other words, they froze their bodies, put them in a cryobed, and traveled for years without aging. Yes, this sounds amazing, but we still don't have the technology to do that. Our bodies are mainly made out of water, right? And when you freeze water, it expands. That's why you should never leave soda cans unattended in your freezer. Right now, if we froze a person's body, the water inside of it would expand, harming tissues and organs. So no, we can't cryosleep our way into interstellar travel. Not yet, at least. Here's a crazy thought. What would happen if an astronaut took a drone with him on one of their spacewalks? Unless it's a NASA-designed drone, maybe the thing would freeze and burn like humans would if they went into space without a suit. But hey, a person can dream, can't they?
Chihilski's star was discovered in the 1960s. Since then, astronomers have been intrigued by its unique chemical makeup. The star is suspected to contain ultra-rare elements, verging on the almost impossible. Using special equipment on the European Southern Observatory's telescope in Chile, researchers took readings of the star's magnetic field. They discovered that the star's rotation period, which is the time it takes to finish one revolution on its axis, stretches out over almost 200 years, which is super slow. Of course, there are even more bizarre objects called apstars. They're a chemically interesting category of stars that rotate extremely slowly, with one rotation taking up to 1,000 years. What makes these stars even more peculiar is a wide range of chemical elements astronomers detect when analyzing their stellar spectrums. But if we look at Chihilski's star, we'll see that it's both similar to and different from other apstars. It contains unusually low amounts of iron and nickel. Our Sun has 10 times more and incredibly high amounts of rare, heavy elements. Those might include strontium, cesium, and neodymium, as well as at least 2 undiscovered elements. They wouldn't occur through any natural processes we currently understand. There's a hypothesis that the presence of such heavy elements could be caused by a star's unseen companion, like a neutron star. Some people go as far as to say that such an incredible chemical makeup could be a sign of an alien technosignature. Any specialist will tell you that it's the strangest stellar spectrum they've ever observed. Some even claim that there are so many chemical indicator lines you can't immediately understand what you're looking at while observing the star's spectrum. Chihilski's star also contains high levels of radioactive elements that take a few thousand years to decay. And here's where another mystery lies. They should have long vanished from the star. After all, it's almost 1.5 billion years old. Scientists haven't managed to figure out the reason for the presence of these elements yet. Maybe it's the combination of the star's rare qualities. It spins very slowly, it's hot, and it has a strong magnetic field. This could raise to the surface atoms that would normally be mixed inside the star. There's another theory that explains the presence of these radioactive elements. They could be there as if they were themselves decayed forms of ultra-heavy elements that we haven't discovered yet. So far, no one has been able to prove this theory. Even the discovery of Chihilski's star's super slow rotation doesn't bring us closer to the answer. It's obvious that there's a lot to learn about the bizarre star, and who knows which secret it still has up its sleeve. Another not less mysterious star is called Tabby's star. It's a sun-like orb around 1,500 light-years away from Earth, sitting in Cygnus the Swan. Unlike our Sun, this star dims randomly by 5 to 22%, and it lasts for days at a time. The reason could be a giant planet passing in front of the star, but then the eclipses would be more regular and not so random. And if it was a Jupiter-sized planet, it would also need to block around 1% of the star's light, which would make it unique and unlike anything we know. After American astronomer Tabitha Boyajian discovered the star's massive and irregular fluctuations in 2015, further observations followed. They show that the overall magnitude of the star has been gradually dimming over the years. Some theories trying to explain this phenomenon are quite believable. For example, some scientists think that these brightness changes are intrinsic to the star. They could be caused by its magnetism or changes in heat flow in its interior. Other ideas are more daring, including some kinds of activity of an extraterrestrial civilization, One of the most plausible theories, though, is that the dimming is caused by the chunks of an orphaned exomoon. It could have been pulled away from its parent planet by gravitational interactions with Tabby's star. As the moon approached the star, it exploded, sending dust clouds into stellar orbit. These countless chunks of rock and dust are now moving between Tabby's star and Earth in a giant, clumpy cloud. It could indeed explain why we observe such irregular brightness variations. Usually, when astronomers spot a spiral arm structure, it turns out to be a galaxy. But not in this case. SAO 206462, located 460 light-years away from our home planet, is a young star. It's surrounded by a circular disk of gas and clearly defined spiral arms. The bizarre star was spotted during an exoplanet search with the help of the Subaru telescope located in Hawaii. Instead of finding fully fledged planets around a young star, astronomers discovered planets that were still in formation. These baby planets are growing out of the disk of gas and dust surrounding the star. The disk extends out to around 80 astronomical units, which is twice the orbit of Pluto. At least 2 of these planets have stretched the disk into its extremely unusual spiral shape. A different planet is responsible for each arm. In our home galaxy, there's a giant star that is a real stellar wind machine. At the moment, this monster is just waiting to burst and send a wave of radiation and hot gas towards Earth. All because it's a Wolf Rayet, a star which is at that precarious point before it goes supernova. Its core doesn't have any more helium left to burn. Instead, the star is forced to churn through much heavier elements, for example, oxygen. Unfortunately, it disrupts the careful balance between gravity and fusion, leading to the star shedding its layers. When the oxygen eventually runs out, the star will go supernova, but this time the show will be different. The thing is, WR104 is 1/2 of a binary pair, which means that 2 stars are feeding into each other, spinning up their stellar winds. It will continue until they start going incredibly fast. Is the potential explosion going to harm Earth? On the one hand, we're far away enough for even a directed supernova to not hurt our planet. At the same time, there's a threat of an extremely dangerous gamma-ray burst. Luckily for us, it takes a very specific and unlikely train of events for a Wolf Rayet to produce a gamma-ray burst. Plus, even if it does, the star might be pointed far away enough for the danger to miss us. Anyway, astronomers are still watching the star, just in case. A star sitting in the constellation of Centaurus keeps a secret not many know about. At first glance, it looks like a dim white dwarf, but when astronomers analyzed it, it turns out to be incredibly dense. Take the mass of the Sun and cram it into something that is only 1/3 the diameter of Earth. This space wonder is also rather cool. Its core temperature is a mere 11,900 degrees Fahrenheit. For comparison, the Sun's core temperature is around 27 million degrees Fahrenheit. At such low temperatures, stars begin to vibrate. And then, scientists can use these vibrations to sneak a peek inside a star. And in the case with the star in question, which was later named Lucy, they discovered that its carbon core had crystallized. In other words, it formed a giant diamond 10 billion trillion carats in size. Since the discovery of Lucy, a few other crystallized stars have been spotted. Some of them have diamond hearts the size of our planet. The last bizarre star for today is called Vega, and it's squashed. The star's bulging waistline is caused by an extremely high spin rate. Vega rotates once every 12.5 hours. This pushes the material around its equator outward. It also leads to the phenomenon known as gravity darkening, when stellar material further from the center of the star experiences less gravity, which makes it cooler and darker. So when Vega faces Earth pole end on, it looks perfectly round. But the dark halo around its middle is a telltale sign of Vega's oblate shape.
Back in 2008, astronomers found a mysterious something orbiting a star called Fomalhaut. This star is very bright and sits about 25 light-years away from us. Trillions of miles, sure, but pretty close in space terms. It's in the constellation Southern Fish, the one that looks like a single fish floating in the southern night sky. It's a small and relatively dim constellation, but Fomalhaut is what makes it so special. In Arabic, this means mouth of the fish, and you might guess where that name comes from. It's the brightest star in the constellation. If you're in the southern hemisphere, you can easily spot Fomalhaut with the naked eye. For people in the northern hemisphere, it's visible in the fall, low on the southern horizon. But this constellation has a beautiful story. The myth says that this fish is the one that saved the deity Dursido, who had fallen into a lake. So it became the symbol of rescue and protection. The fish in Pisces is said to be the offspring of the southern fish, forming a kind of family. At the same time, Fomalhaut is sometimes called the lonely star because it's one of the brightest stars in its part of the sky, but it doesn't have many bright neighbors. Hey, I can relate to that. Nah, just kidding. Fomalhaut is also a young star. It's only about 440 million years old. Now that sounds like a lot, but our Sun, in comparison, is 4.6 billion years old. And finally, it's surrounded by a giant ring of dust and gas. This is called a debris disk. It's like a dust cloud that serves as the birthplace of planets. It's like the Kuiper belt in our own solar system, where Pluto lives, but on a much grander scale. But then, astronomers noticed something odd about this disk. It wasn't evenly shaped. This means that there's something that influences gravity nearby. A planet, perhaps? And when they took pictures of the disk, they found a faint glowing dot inside it. That was our mysterious gravity center, Fomalhaut B, or how they named it later, Dagon. They immediately thought it was a planet. In 2008, it was a huge deal because scientists captured an actual image of it using the Hubble Space Telescope. Now that's a super rare thing, especially for objects outside our solar system, not to mention such tiny things as planets. And the photos were fascinating. At first, everyone was excited about the new world. Scientists thought that Dagon was a massive planet, something maybe like Jupiter, a gas giant. They even guessed that it had an oval-shaped orbit, which means that it would take about 1,700 years to go around its star just once. That's one of the craziest orbits we've ever seen. But as they kept studying Dagon, they noticed that things don't add up. For starters, they couldn't find it in infrared light. Now, planets that big usually give off heat, and telescopes like Spitzer, which look for heat signals, found nothing. Weird, right? Also, the planet was moving too strangely. Its orbit didn't match what you'd expect if it were shaping the dust ring. So scientists started thinking, maybe it's not a planet at all. And as the doubts creeped in, the hype calmed down. In 2020, they noticed another strange thing about Dagon. It was getting dimmer and spreading out. And well, planets don't usually do that, but clouds of dust do. This led to a new idea. What if Dagon isn't a planet, but the result of a massive collision? Imagine two big chunks of ice or rock smashing into each other at incredible speeds. That's what they think happened here, a giant space crash that led to lots of debris. That's how it got officially removed from the list of exoplanets. But then, in 2023, the new James Webb Space Telescope, which is even more powerful than Hubble, decided to take a closer look at Dagon. And when scientists looked at the data, they jumped back into the previous debates. Wait, it might be the planet after all. All this scientific back and forth led to Dagon getting dubbed the zombie planet. But after a while, astronomers finally found the middle ground. Dagon really turned out to be a dust cloud that's slowly disappearing, but there could still be hidden planets in the system. There's another ring of dust closer to the star that might be shaped by an unseen planet. There are many mysterious weird planets out there. Trace 2b orbits a star 750 light-years away from Earth, much farther out than our Dagon. It's in a region of the sky that's been heavily studied by planet hunters. It was first discovered in 2006 by the Transatlantic Exoplanet Survey, an observatory with a bunch of cool telescopes that are used to find planets. They use a witty method for it. They observe the stars, and when they see unexpected dips in brightness, that means that something must be passing in front of the star, making it a wee bit darker. This is called the transit method of the planet discovery. When Trace 2b was spotted that way, scientists took a closer look and confirmed it. It had a certain gravity pull that caused its star to wobble. But that also means that the planet should be gigantic, probably a gas giant like Jupiter or Saturn. But, unlike Jupiter, Trace 2b is much closer to its star. This makes it a special type of a planet called hot Jupiter. That's what we call gas giants that orbit so close to their stars that their atmospheres are scorched to extreme temperatures. Imagine if Jupiter was not only horrifyingly massive, but also almost burning. This planet is tidally locked to its star. This means that it always faces the sun with one side, just like we can only see one side of our moon. Its day side is blisteringly hot, but even the cooler night side has temperatures around 2,900 degrees Fahrenheit. But there was something very eerie about this new world. What really made it stand out was its albedo, a measure of how much light the planet reflects. Most planets, like Jupiter or even Earth, reflect a good amount of light thanks to clouds, ice, and other stuff. This is what allows us to see those planets after all. But Trace 2b is almost completely black. For some reason, it reflects less than 1% of the light that hits it. It's darker than coal or fresh asphalt. So, why is that? After some thought, astronomers think it might be because of its atmosphere. Jupiter has bright reflective clouds of a gas called ammonia, but Trace 2b probably doesn't have those. Since it's so close to its star, they'd burn up and get stripped away. So, its atmosphere might be made up of chemicals like sodium, potassium, or titanium oxide. All of this stuff absorbs a lot of light, and if you look directly at that planet, you'd see it almost as a black hole. What's even more horrifying is that if you were floating in it, since it doesn't have a solid surface, these elements could make the sky above look like an endless void, even if it's daytime. Though you'd probably still see its star, even it would be completely surrounded by blackness, like light at the end of a tunnel. In that case, shouldn't it be completely invisible? Well, it kind of is. But it also emits a faint red glow, likely due to its scorching high temperature. And even though scientists have studied Trace 2b for years, some questions remain unanswered. Why is it the darkest planet we've ever found? Is it possible that there are some unknown chemicals in its atmosphere? What hides beneath the darkness? These Jupiter-like planets are often crazy, like WASP 76b, for example. This is another gas giant located about 640 light-years away, this time in the constellation Pisces. Just like Trace 2b, this exoplanet is tidally locked. One side has a temperature of over 4,000 degrees Fahrenheit, while the other side remains in constant darkness. But what's crazy about it is that the extreme heat on the day side vaporizes metals like iron. The planet has insanely strong winds, and they blow this molten iron to the colder side. And you guessed it, the iron gets solid under colder temperatures, and we end up with a horrifying iron rain. All this stuff sounds like science fiction, but it's real, waiting to be explored.
Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle.
Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal poor star. It suggests that the star that collapsed and formed BH3 was metal poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course, the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state.
It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.
The Sun isn't technically the center of our solar system. It's in a space called the barycenter. It depends on which planet you're standing in. The barycenter is usually closest to the object with the greater mass. So, since we're on Earth, the true center of the solar system is the Sun, but not the center of it. With respect to Jupiter, the barycenter is actually outside the Sun's surface. Jupiter is 318 times bigger than Earth, so the balance is different. The planets don't really revolve around the Sun, but around their common center of mass. Imagine balancing a pencil on the tip of your finger. You'd have to place it right in the center so that it doesn't tip on each side. Because the pencil has its mass equally distributed, it's easy to assume that everything balances its way like that, especially in outer space. But try balancing a hammer on the tip of your toe. Chances are you'll walk out of here with a broken toe. Its true barycenter is close to the hammerhead rather than the actual center where you'd grip it. Earth and the Sun's barycenter is like that hammer. The center of mass is more or less in the center of the object. Realistically, if the Sun were to rotate around Earth, then our little blue planet would have to be just as big as the Sun, or bigger. We can't disregard the other planets in our solar system, which means they all will have to rotate around us as well. But in the ancient days, bright minds always thought everything revolved around the Earth. They called this the geocentric model, and this made sense to them because it looked like everything above us was spinning around us. The Sun and the Moon played vital roles in human history, and we didn't feel insignificant in the universe until way later on. In ancient Greece and the Middle Ages, the big brains used the geocentric model to study space. It wasn't until the 16th century that that model changed. Back in those times, they couldn't even imagine that everything revolved around the Sun. And they didn't have the knowledge to back any of this up. The Earth can't be the center of the solar system because it's not large enough for the job. For the conditions to suit the enormous size, life would have evolved differently. We'd probably be less dependent on oxygen. Some animals, like whales and dolphins, can stay for hours without taking a single breath. They can even sleep underwater. So the humans of the sun-sized Earth would have specialized lungs and wouldn't need to constantly be taking in air. It means that the plant life would be limited, with just a few shrubs here and there. There are trillions of trees around the world, but the main contributor to producing oxygen is the algae in the ocean. With such vast real estate of oceans and seas, the algae sitting on top are pumping out the air we breathe. Oxygen wouldn't be so abundant on this planet, but our breathing mechanisms might rely on carbon dioxide, another common gas found on other planets. If the planet is hot, then water will be scarce. We would only find it on certain parts of the planet, like mountaintops. The ground would be too scorched for anything to survive in properly. We can forget about seasons as well. The sun is currently just large enough to give us what we need. But since the Earth would be so large, and the sun would be another celestial body emanating heat, we'd always feel like we're inside a microwave. The days and nights will be different, and not much precipitation will happen. With so much heat produced in the core, earthquakes and volcanoes would likely erupt all the time. The surface would practically be a scorching plain of red magma floating around. This would be the true red planet. But if we had the same landscape like on Earth, living somewhere near the mountains could save you. The mountains would still be embedded in the core, but it would be better than staying on the ground. Some of the mountain peaks could even be 100 times taller than Mount Everest. The canyons could be so deep that the Mariana Trench would feel just like a little rupture. Animals would also behave and look different. Cold-blooded animals would have to soak up as little sun as possible so they don't burn. Animals would have to rely on migration to find water in distant lands. Birds can fly for hundreds of miles for migration season, so we'd probably see certain sleek-looking birds speeding through the air. But because gravity would be so strong on the colossal-sized Earth, the flying animals would need thinner bones and a thinner core just to take flight. The real survivors would be the microorganisms. They can live in extreme temperatures and pressures and can live without oxygen for a good while. The nights would be dark since there wouldn't be any moon to reflect the sunlight. The moon would most probably be on the opposite side of where the sun is shining, so it would forever be a floating ball in the sky. The Earth's rotational speed is the fastest at the equator, so if all the planets and the sun rotated around us, then our rotation wouldn't be so significant. New weather patterns wouldn't be good for crops. Humans would have evolved differently from what we are like now. We'd probably be shorter and stockier since gravity is so strong. And because of the soaring temperatures, we'd probably live in caves all around the world. The strongest ones would have migrated to the mountains. We'd probably have the same evolutionary path as we do now, but other physical features might be different. Our pigment would likely look different to combat the heat. The desert fox has large ears for hearing out predators and for cooling itself down in the scorching desert heat. It's possible that we would also have bigger ears than what we have now for the latter reason. We'd be a lot stronger than we are, and our bones would be thick and tough to break. Gravity is one of the key components to developing our bone density and muscle mass. This means we would unlikely need tools for hunting. This would have delayed the Bronze Age and modern civilization as we know it. With little vegetation, standing upright wouldn't be so necessary to find predators around us. We wouldn't be the fastest runners either, but we'd be strong enough to fight off a pack of strange-looking wolves. And if the Earth was supersized, then it's possible that multiple species of humans would be roaming the land in isolated areas. Some human species would grow and evolve into the intelligent thinkers of today, but some would remain the same. And some creatures from the past would still be around, unchanged. Sharks would have been around since the dinosaurs era. They wouldn't have to change their form or adapt because of their dominance. Other animals would remain the same because of their isolation. The Galapagos Island hosts some unique animals because they've been alone for so long. Without proper predators constantly lurking around them, they don't fear humans. The new mega-sized Earth would have areas as large as Asia filled with isolated animals that could remain the exact same as when they first appeared. The human species of those regions would also remain the same, since they wouldn't have moved or experimented with anything. Their diet would remain the same, and they would get used to the climate they're in. Technology would also have flourished differently in various parts of the planet. With some areas in complete isolation, they wouldn't have access to new gadgets and inventions. It would be like living on a planet with different eras in the present day. Other areas would be so advanced, they might even be flying themselves outside the planet in search of truth and answers. Our gravity is good enough for us to live properly and develop life, but if we pumped up our size to that of Jupiter, then gravity would crush us. And being the size of the Sun, Earth wouldn't even be a planet, but a brown dwarf, and would constantly be burning until it became a new sun. As of now, Earth is so small in our universe that we're practically like a grain of sand in the desert. On a cosmic level, we're an insignificant contribution to this universe. Hop on board! Hurry, we don't have much time. We're on a cosmic journey to find the biggest star in the universe. The first star we pass is our own sun. By far, not the biggest one out there, but it's still massive. You could fit 1 million Earths inside it. That means, if you think of the sun like a basketball, Earth would be half the size of a pencil eraser. If we put all the planets on one side of a scale and the sun on the other, the planets wouldn't stand a chance. The sun makes up 99.9% of all the mass in the entire solar system. Mass is basically how much stuff or matter something is made from, and it's what you can thank for stars shining. You see, the more matter in a star, the thicker and hotter its core becomes. This starts a chain of chemical reactions. Hydrogen atoms get smashed into each other to form helium, releasing an incredible amount of energy. That's the star's light and heat. So, bigger stars also equal brighter ones. But with all those reactions going on, this shortens a star's lifespan. When it starts to run out of fuel, the star will enter the giant phase. It'll expand and turn red. Which brings us back to the task at hand. The biggest star we'll find is likely to be on the edge of its life. Switching on our hyper light engines, we soon arrive at the Lumen 16 system. Here, we'll find one of the smallest stars out there, a brown dwarf. Small here means about the size of Jupiter, but they're small for stars. Brown dwarfs are also called failed stars because they don't have enough mass for those chemical reactions. That means they're not as bright, but they're super dense. All the matter in them is packed together so tightly, they weigh 80 times more than Jupiter, even being the same size. And if you think that's something, just look at a white dwarf, even more tightly packed. This one here is Sirius B. It's also about the size of Jupiter, but it'd weigh as much as the sun. It emits a dim white light. Once it runs out of gas, it'll turn red and cool down. Now let's fly closer to its giant neighbor, Sirius A. You easily see this star from Earth, no telescope needed. Twice heavier and more than 1.5 times wider than our sun, it's the brightest star in our night sky. Now we fly 550 light-years away from Earth to the constellation Cassiopeia. Almost 100 years ago, a cosmic explosion happened here. It expanded the atmosphere of the star Gamma Cassiopeia, and some gases were thrown into space. After that, it became the brightest star in the constellation. It's 10 times wider than our sun. On to the famous North Star. Funny enough, different stars have had this title over the years, and more will take it in the future. That's because Earth's pole star changes every 26,000 years. Imagine our planet like a spinning top. The northern pole will shift around in a little circle, pointing at different stars to the true north. The current one is a supergiant 37 times wider and 5 times heavier than our sun. It's easy to find in the night sky. It's on the very tip of the Little Dipper's handle. Get ready now. We're setting off for the eye of the storm, the center of our Milky Way galaxy. To see the next star, we need to switch to infrared mode. This pistol star is hiding from us in space dust. In just 20 seconds, it emits as much light as our home star does in an entire year. And its size is jaw-dropping. It's 420 times wider than the Sun. But it's still not the most luminous star known to humanity. That would be a blue supergiant in the constellation Triangulum. Meet B416. It's almost 10 million times brighter than the Sun. But the brighter a star, the faster it burns up all its fuel, and the shorter its life. Compared with a red dwarf that barely glows and burns fuel much more slowly, its life will be hundreds of thousands of times shorter. 3,400 light-years from Earth, there's one of the rarest celestial bodies in the universe. It's a yellow hypergiant called Rho Cassiopeia. Among the countless stars in our galaxy, there are only a couple dozen of these. And even though this star is extremely far away from our planet, you can still see it in the sky without needing a telescope. That's because it's 300,000 times brighter than our Sun. It also helps that the thing is 900 times wider than our home star, too. And its color tells us that its fuel reserves will last for a long time. When Rho Cassiopeia starts to turn red and expand, it'll be one of the biggest stars in the entire universe. Now, we move to the constellation Orion. The star is in our sights. Betelgeuse, one of the largest ones visible to the unaided eye. 700 times the size of our Sun. If it took our star's place, its surface would touch the asteroid belt. That's between the orbits of Jupiter and Mars. It would engulf the 4 inner planets, Earth included. But this star has astronomers very excited. They predict Betelgeuse will explode in a fantastic celestial show in the next 10,000 years. It'll be the greatest astronomical event of all time because we'll be able to observe a supernova at a close but safe enough distance. The exploding star will shine as bright as a half moon. It'll be visible in the daytime sky for a year and at night for several more. Now we venture to stars that exceed the Sun's width 1,000 times. Mu Cephei is a hypergiant boasting the title of the reddest known star. Its color tells us that the fuel gauge is getting closer and closer to empty, but it's still so big that it could hold 1 billion suns in it. And because of its mass, this star will eventually become a supernova or even a black hole. Let's take a trip of almost 4,000 light-years from home. Here it is, a red supergiant called VY Canis Majoris. It's one of the biggest and brightest stars of the Milky Way. It could fit 3 billion suns. And even though it's so huge, this thing is surprisingly light, only 17 weights of the Sun. In the context of celestial bodies, you could call this star an inflated balloon. In the next 100,000 years, VY Canis Majoris will explode in a hypernova. Gamma radiation will destroy all life in the local part of the universe. But this star is so far from our solar system that it wouldn't mean any harm to us. If we placed MY Cephei in the center of our solar system, it would bulge all the way out to Saturn's orbit. To remind you just how far away Saturn is, think of it this way. It takes the Sun's light 8 minutes to reach Earth. To get to Saturn, it takes well over an hour. Compared to this massive star, the Sun is just a grain of sand. It's one of the most luminous and reddest stars in our universe. The bigger and redder the star, the closer it is to its end. So, we're not looking at just a titan of the universe, but also one of the oldest celestial bodies out there. The second biggest star in the universe is UY Scuti. It's about 1.5 billion miles wide, 16 times the distance from the Earth to the Sun. This is a pulsating variable star. Its brightness changes about every 2 years. UY Scuti is a record breaker in fuel combustion per year. Scientists expect it to evolve back to hotter temperatures like a yellow giant. Our journey is coming to an end. Before us, we behold Stephenson 218. It takes 20,000 years for light from this star to reach Earth. It's hard not to see this red supergiant on our tiny terrestrial home. It's 2,150 times wider than our Sun. We'd need 10 billion suns to fill its volume. For comparison, the average beach contains only about 5 billion grains of sand. A recent study suggests the universe is similar to your brain, only at a much, much larger scale. The brain's neural network contains about 86 billion neurons. The observable universe has at least 100 billion galaxies. Both galaxies and neurons have a similar structure. It's a complex web of nodes linking up long thread-like fibers. But in each of these systems, the fibers make up a mere 30% of the total mass, and the remaining 70% are either water in the brain or dark energy in the universe. The ways that galaxies and webs of neurons connect with one another are surprisingly similar. In both cases, the process follows the same physical principles. At the same time, some researchers claim the resemblance between the brain and the universe is only superficial. Your mind perceives tiny details and joins them, and then it comes up with a conclusion that has nothing in common with reality, like the brain is a mini-universe. In billions of years, the universe is likely to expand so much that we won't be able to see any stars in the sky. To turn Earth into a black hole, you'd have to squeeze it until it was the size of a marble. And if you wanted the sun to become a black hole, you'd have to compress it until it's no more than 4 miles across. A starburst galaxy is a galaxy that's forming tons of new stars at breakneck speed. It usually happens after 2 galaxies merge into one. While Earth has only one natural satellite, Jupiter is surrounded by at least 79 moons. In the universe, there are not only dwarf planets, but also dwarf galaxies. They have from 1,000 to a few billion stars. For comparison, the Milky Way galaxy is made up of 250 to 400 billion stars. A supermassive black hole 250 million light-years away from Earth hums the deepest sound ever detected from any object in the universe. It's 1 quadrillion, which is 1 with 15 zeros, times deeper than what the human ear can hear. Planet Carinae B is 670 light-years away from Earth. It's an ultra-hot Jupiter. Those are giant, scorching hot planets with a mass similar to that of Jupiter. On Carinae B, the heat is so great on the day side of the planet, it tears molecules apart. Any liquid floating in outer space forms itself into a sphere. It also happens in low Earth orbit. Our home Milky Way galaxy is more than 105,000 light-years across. All the planets of the solar system would fit between Earth and the Moon with some space to spare. Black holes spaghettify things. It happens when something gets past the point of no return. Then the black hole's gravitational pull starts to stretch this object in one direction and squeeze in another. The first celestial body that astronomers identified as a spiral was the Whirlpool Galaxy. Its long arms are made of gas and stars, and everything is sprinkled with fine space dust. When you're on Earth, you can only see 5% of the universe. A star coming too close to a black hole can be torn apart by its gravitational force. WASP 12b is a giant planet 1,400 light-years away from Earth. It's made up mostly of gas. Unfortunately, the planet is doomed. It orbits too close to its parent star. In about 10 million years, WASP 12b will be swallowed by its greedy sun. Our Milky Way galaxy and the Andromeda galaxy, its closest neighbor, are going to meet in a bit less than 4 billion years. When they collide, they'll form one huge elliptical galaxy. One of Saturn's smaller moons, Enceladus, reflects almost 90% of the sun's light. It makes the moon one of the brightest objects in the solar system. But since it reflects sunlight instead of absorbing it, the temperatures on Enceladus's icy surface drop to negative 330 degrees Fahrenheit. The highest mountain in the solar system is Olympus Mons on Mars. It's 3 times as high as Mount Everest. If you were standing on top of Olympus Mons, its slopes would be hidden by the planet's curvature. In our solar system, Mercury and Venus are the only two planets without moons. Scientists who are planning to send droids to Mars want to load the machines with lots of heavy equipment. The droids will also be built from stronger materials, all because of the relatively low gravity on the red planet. Everything on Mars is almost 3 times lighter than on Earth. Pluto's largest moon is half the size of the dwarf planet itself. This makes Charon, that's the moon's name, the largest known satellite relative to its parent size. There are 3 golf balls on the moon. They were launched during the Apollo 14 mission. Mathematicians claim white holes might exist, even though scientists haven't found one yet. If you came across a white hole, you wouldn't be able to enter it from the outside, but you'd see light and matter escaping from within. On our planet, one full rotation takes 1 day, but the Sun is so enormous that it needs 25 to 35 Earth days to make one rotation. The Moon is not a perfect sphere. It's shaped more like an egg because of the Earth's gravity. Spacesuits protect astronauts from huge temperature differences during spacewalks, from negative 250 degrees Fahrenheit to positive 250 degrees Fahrenheit. A neutron star gets born after a supernova collapses. After birth, it rotates extremely fast, about 60 times per second. But this rate can sometimes grow up to 600 times per second. In 2007, astronomers started to receive ultra-bright and ultra-strong radio signals. Named fast radio bursts, they were coming from somewhere billions of light years away. When astronauts are in space, they often see random flashes of light. They occur when cosmic rays hit the optic nerve in the eye. If you traveled around Pluto's equator, it would be the same distance as walking from Rome to New York City. If you visited GJ 504b, a planet located a mere 57 light-years away from Earth, you'd see that the planet is glowing. It's because of the heat left after its formation. The planet's color is a dull magenta, like a dark cherry blossom. Jupiter has the shortest day of all the planets in the solar system. It lasts just 9 hours and 55 minutes. Because of its fast rotation, Jupiter isn't a perfect sphere. It's a bit flattened. Venus has more volcanoes than any other planet in the solar system. There are at least 1,600 of them on the planet's surface, but most of them are extinct. Mercury has wrinkles. When its iron core was cooling, the planet's crust contracted. It made the surface of the planet uneven. Nuclear pasta found inside neutron stars is believed to be the strongest substance in the universe. These noodles of neutrons can be 10 billion times stronger than steel. Some astronomers believe black holes might have no event horizon, aka the point of no return. Instead, there might be the apparent horizon. It can only trap stuff for some time. Later, matter or energy escapes, but in a different form. Each Apollo mission needed 15 spacesuits. Each member of the 3-person main crew needed 3 suits. One was for training, the second for flight, and there was also a backup suit, in case something went wrong with the flight suit. And each of the 3 members of the backup crew had 2 spacesuits, one for training and one for flight. Scientists believe Mercury might still have a partially molten core. It could explain why the planet has a magnetic field, even if it's just 1% as strong as Earth's. Dust storms on Mars are the most severe in the whole solar system. They can be raging for months on end. On planet Kepler 16b, which is 245 light-years away from Earth, not one, but 2 suns set over the horizon. The planet is as massive as our Saturn, but has a higher density. It takes 45 minutes to put on a spacesuit. After it's done, an astronaut needs another hour to adapt to new conditions. Earth-grazing fireballs are bright meteors that enter the Earth's atmosphere but then leave it again. Triton, one of Neptune's moons, orbits the planet backward. It's the only big moon of any known planet to do so. Triton is also gradually getting closer to Neptune. Experts think that, eventually, the moon will be pulled apart by Neptune's gravity, and then it'll form a ring around the gas giant. Dwarf planet Haumea, which is further from Earth than Neptune, is truly bizarre. It's orbiting in the Kuiper Belt, a donut-shaped ring of ice objects circling the Sun. Haumea has 2 moons, a weirdly elongated shape, and a day that lasts 4 Earth hours. But the coolest thing, the dwarf planet is surrounded by incredibly thin rings. They're likely the result of an ancient collision. It takes Neptune almost 165 Earth years to make one full orbit around the Sun. In other words, since the gas giant was discovered in 1846, it's only circled the Sun once.
Stargazers, come up here, because I have exciting news. Astronomers have just completed the full mapping of 2 pairs of stars outside our Milky Way galaxy that are chowing down on their stellar neighbors. Not only does it give us a better understanding of stars in general, but it can also help us measure distance in the night sky. Did you know that more than half of the stars in our Milky Way are paired? And while it's unlikely that other galaxies have a significant number of binary stars too, they're usually too faint to see. But these so-called symbiotic stars, where one star consumes the other, are extremely bright and easier to observe. And, according to scientists, measuring the orbits of these symbiotic star systems is an essential step towards learning whether other galaxies create binary stars like those in our Milky Way. Now, let's get down to the nitty-gritty. A pair of stars may be born together, but due to their masses, they age differently. The more massive one burns through its material faster, reaching the end of its lifetime first, and leaves behind a compact white dwarf. White dwarfs are small and dim, but can pack the mass of the Sun into an object the size of Earth. If close enough, their gravity can pull material from their companion, creating a signal that astronomers can identify from far away. Draco C1 and Lin 358 are the symbiotic stars that have been fully mapped. The stars in Draco C1 take roughly 3 Earth years to orbit one another, while Lin 358's components take just over 2. These are the first full orbital measurements of any symbiotic star system outside the Milky Way. The new measurements will help astronomers better understand star formations in other galaxies. In some symbiotic stars, the white dwarf can slurp enough material from its companion that it explodes in a supernova. These supernovae are incredibly bright and can be seen across the universe. They all start out with the same brightness for a nearby observer, making them like a sort of standard candle for measuring the universe. While Draco C1 and Lin 358 are unlikely to explode as supernovae anytime soon, understanding how they work can provide us with a better understanding of how these standard candles evolve. If you're here to complete your knowledge of weird stars in the universe, don't be disappointed. We're not finished just yet. Have you ever wondered about the biggest stars in the universe? Scientists have recently discovered a gigantic star called UY Scuti. This bad boy is located about 9,500 light-years away from Earth and is truly out of this world. It's about 1,700 times larger than our Sun, which means if it were in our solar system, it would reach past Jupiter's orbit. There's more. UY Scuti isn't just massive, it's also super bright. It's what scientists call a red supergiant, and it shines with a brightness of about 340,000 times that of our Sun. If you're thinking about getting a tan from this star, think again though. It's way too far away for that. How does a star like UY Scuti even form, you might wonder? Well, it starts out like any other star. A cloud of gas and dust collapses under its gravity and starts to heat up. Eventually, the temperature becomes hot enough in the core of the cloud to ignite nuclear fusion, and a star is born. But UY Scuti didn't stop there. It kept devouring more and more gas and dust, growing larger and larger. This process continued until it became the giant we know today. As fascinating as UY Scuti is, it's not the only big star out there. There are others, like VY Canis Majoris, which was once thought to be the biggest star until UY Scuti stole the show. VY Canis Majoris is still a force to be reckoned with, though. It's about 1,400 times larger than our Sun, and located about 5,000 light-years away from us. But here's the kicker. Stars like UY Scuti and VY Canis Majoris aren't even the biggest things in the universe, not by a long shot. There are objects called hypergiants that make these stars look like ants in comparison. One such hypergiant is Stephenson 218, located about 20,000 light-years away. It's about 2,150 times larger than our Sun, and shines with the brightness of 7 million suns. And just when you thought things couldn't get any crazier, there's a mysterious object called the Great Attractor that's pulling everything in our local group of galaxies towards it. We don't know what it is or what's causing it, but one theory is that it's a massive cluster of hypergiants. We'd be minuscule in comparison. The next star is so metal, it's practically headbanging all the time. Jokes aside, scientists have discovered a star that's called a heavy metal subdwarf. Now that's a band name. It's a type of star that's seriously heavy metal. This star has more metal in its composition than any other star we've seen before. Such stars are said to contain metal elements like iron, nickel, and chromium. This heavy metal subdwarf has about 10,000 times more iron than our Sun. In their discovery, astronomers used a technique called spectroscopy, which involves analyzing the light that comes from the star to determine what elements it's made of. By looking at the spectrum of light, scientists were able to see that this star had an unusual amount of metal in its composition. There's more. This heavy metal subdwarf isn't just a regular star with a lot of metal. It's also really weird in other ways. For one thing, it's smaller and cooler than our Sun. And for another, it's really old. We're talking about a star that's been around for almost as long as the universe itself. What does this all mean? Well, scientists are hoping that by studying this heavy metal subdwarf, they can learn more about the early universe. Since this star is so old that it was around when the universe was just beginning to form, it's seen a lot of stuff. By studying its composition and characteristics, scientists can get a better understanding of what the universe was like in its early days. This next star is one of the coolest things in outer space. Her name is Vega, and it's one of the brightest stars in the night sky. Some recognize it as the shiny point of light in the constellation Lyra. And get this, it's only about 25 light-years away from us, which in astronomical terms is practically next door. Scientists have been studying Vega for a long time, and they've learned some pretty interesting things. For starters, Vega is a young star, only a few 100 million years old. That might sound like a long time, but compared to our Sun, which is around 4.6 billion years old, Vega is practically a newborn. Vega is also a very hot star, with a surface temperature of around 17,000 degrees Fahrenheit. To put that into perspective, the surface of our Sun is only about 10,000 degrees Fahrenheit. So if you think it's hot outside today, just be glad you're not hanging out on Vega. Another interesting thing about this star is that it's surrounded by a disk of dust and gas. This disk is called a debris disk because it's made up of leftover material from when the star formed. Scientists think that this debris disk is similar to the one that surrounded our solar system when it was young. Vega is also a source of cosmic rays. These rays are high-energy particles that zip around space at incredible speeds. They're made up of protons, electrons, and other particles, and scientists aren't exactly sure where they come from. But they do know that Vega is one of the places where cosmic rays originate. But wait, there's more! Vega is also a famous star in pop culture. It's been used in a lot of movies and